Good morning. We were discussing summation of series yesterday. Now we'll today look at some other strategy like method of difference. Next. What is this method of difference? What we do? Let's see it with one example. You recall that we summed up this series. We summed up this series yesterday. You recall what was our strategy? What was our strategy in summing up this series? It's just yesterday we did it. See, what we do is we write the rth term. We write the rth term. What is that equal to? That is equal to r into r plus 1. Is it all right? We express this as difference of two terms. You recall what I did? I wrote it like this. Is it all right? That is what I did was that I expressed a term as difference of two terms which can be easily summed up. All right. So this is one of the strategies which we adopt while summing up some of the series. That is what we do is we write the rth term. We write the rth term in terms of some other terms like AR minus AR plus 1 and sometimes as AR minus 1. All right, we express rth term as difference of two terms, AR minus AR plus 1, AR minus 1. And if you sum it up, what are you going to get? R varying from 1 to n TR, what is that equal to? R varying from 1 to n AR minus 1. And now when you sum it up, what does it become? It can be written as, yes, you look at it, what does it become? If you sum it up, A1 minus A2 plus A2 minus A3 plus A3 minus A4, and you continue like that. You write the last term as AN minus 1. Sorry, AN plus 1. All right, and you will find that these terms are cancelling and you're left with first and the last, that is A1 minus AN plus 1. Okay, this is a strategy which we adopt while summing up series. Recall that I promised that we shall be summing up recall that I promised that we shall be summing up this series once again. Okay, I told you some methods yesterday. All right, now let's look at a method which is like difference. See, what we do is look at it. What is TR here? What is TR? TR is just R. Now we must be able to write this as difference of two things. All right, we must be able to write this as difference of two things, which when added up collapses to just two terms or three terms. Okay, there are several ways which we can adopt. For instance, I can consider this. I can write r plus 1 whole square minus r square. This can be written as 2r plus 1. Isn't it? We can adopt this strategy. Okay, look at it. If I add, what I'm going to get? Let's put it equal to Sn. If I add, what I'm going to get? Put r equal to 1, 2, 3, so on and so forth up to n. All right, you put n is equal to 1, 2, 3, 4, so on and so forth. What do you get? First term will be equal to what? 2 square minus 1 square, that is equal to 2 into 1 plus 1. What is next? 3 square minus 2 square, that is equal to 2 into 2 plus 1. 4 square minus 3 square, that is equal to 2 into 3 plus 1. And you continue like that. What will be the last term? N plus 1 square minus n square, that is equal to 2 into n plus 1. Is it all right? Now you add the terms on the left hand side. If you add the terms on the left hand side, what you're going to get? What is, if you add the terms on the left hand side, what you're going to get? Yes, you will be getting n plus 1 whole square. Is it all right? You will be getting n plus 1 whole square because you will not be able to cancel this term. You will not be able to cancel this one. Isn't it? You will not be able to cancel this one. So you will be getting n plus 1 whole square minus 1 square. That is equal to what? That is equal to 2. You add this column. All right. You add this column. If you add this column, what are you going to get? 1 plus 2 plus 3 up to n. And if you add this numbers, what you're going to get? You're going to get n. Is it all right? And what is this equal to? N square plus 2n plus 1 minus 1, that is 2 into Sn plus n. Simplify, what do you get? See, this one will cancel. You bring this n on this side, you get n square plus n, that is equal to 2 into Sn, which in turn will imply that Sn is equal to half of n into n plus 1. Okay, you will be getting Sn is equal to half of n into n plus 1. So this is a strategy which was used before we came to know of the reversing technique. All right. Now, see, sometimes what we do is that we write R. This is TR. Let's continue with the same problem. I'm telling you an alternative way. All right. I'm telling you an alternative way. You take TR is equal to R. If you take TR is equal to R, think of this, R plus 1 whole square minus R minus 1 whole square. What is that equal to? R plus 1 whole square minus R minus 1 whole square. That is equal to 4R. Is it all right? That's equal to 4R. Okay. Now what you do is you put R equal to 1, 2, 3, n minus 1, comma n. If you do that, what are you going to get? What will be your first term? 2 square minus 0 square, that is equal to 4 into 1. Isn't it? That will be equal to 4 into 1. If you take the next one, that is going to be 3 square minus 1 square, that is going to be 4 into 2. 4 square minus 2 square, that is equal to 4 into 3. You continue like that. You put n minus 1, you will be getting n square minus n minus 2 square. that is equal to 4 into n minus 1, n plus 1 square minus n minus 1 square, that is equal to 4n. Okay. If you add the terms on the left, what do you get? If you add the terms on the left, what are you going to get? See what are the things which are going to get cancelled. See, in this case, you will find that 2 square will get cancelled with this 2 square. And the next will be 5 square minus 3 square. That will cancel this and this. Is it okay? That will cancel this and this. And you continue like that. If you continue like that, you will find that these two terms don't get cancelled. Isn't it? You will find that these two terms don't get cancelled. You will be getting here n plus 1 whole square plus n square. And these two terms don't get cancelled. Minus 1 square. What is that equal to? That is equal to 4, 1 plus 2 plus 3 up to n. Is it all right? Please check. If you have any problem, you can ask it. Okay, simplify, what do you get? If you simplify, what you're going to get? Do you get the required result? N square plus 2n plus 1 plus n square minus 1, that is equal to 4 into Sn. All right. You merge these two, ये cancel हो जाएगा. You will be getting 2n square plus 2n, that is equal to 4Sn. All right. Now, what about this equal to? N square plus n by 2, that is equal to Sn. That means Sn is equal to 1 by 2 n into n plus 1. Okay, so we can adopt this strategy even. That is, what we do is, we express AR as TR plus 1 minus TR minus 1. All right, we can express it as AR TR plus 1 minus TR minus 1. Okay, yesterday, you recall, yesterday, I asked you to find out the sum of this. Isn't it? You know the answer. What is the answer? It is 1 by 6 n into n plus 1 into 2n plus 1. Isn't it? It is 1 by 6 n into n plus 1 into 2n plus 1. How will you reach this? What is going to be your strategy in this case? See, you have learned a technique. You try to express rth term in terms of difference of two terms. Okay, you try to express rth term as difference of two terms. For instance, let's look at this. See, what you do is, you look at this. What is r plus 1 whole cube minus r minus 1 whole cube? What is this going to be? Tell me, r plus 1 whole cube plus minus r minus 1 whole cube. What is that going to be? Yes. It is 6r square plus 2. Isn't it? It is 6r square plus 2. If you simplify r plus 1 whole cube minus r minus 1 whole cube, it is going to be 6r square plus 2. All right. Let's put r equal to 1. What do you get? 2 cube minus 0 cube, that is equal to 6 into 1 square plus 2. Is it all right? Next you put r is equal to 2. What do you get? 3 cube minus 1 cube, this is equal to 6 into 2 square plus 2. Put r is equal to 3. This is 2 cube. Okay, you continue like that as you did in the previous case. What is the last term? That is going to be n plus 1 whole cube minus n minus 1 whole cube, that is equal to 6n square plus 2. Is it all right? What will be the term prior to that? That's going to be n cube okay. No problem. All right. If you add up the left hand side, what do you get? If you add up the left hand side, what do you get? Okay, if you add the left hand side, you will be getting, let's look at the terms which will not cancel. This two terms will not cancel. These two terms will not cancel. That means if we add the left hand side, we shall be getting n plus 1 whole cube plus n cube minus 1, that is equal to 6 times and what is this equal to? Okay, it is 6 times 1 square plus 2 square plus n square, and when you add 2 to 2 n times, you'll be getting 2n. So what is this equal to? This implies n cube plus 3n square plus 3n plus 1 plus n cube, that this is the expansion which I have written here. Now this is n cube and minus 1, that is equal to 6 Sn plus 2n. All right. And what do you get now? You will be getting this n cube plus n cube, that is going to be 2n cube, 3n square as it is. Now what you're left with? This 1 will cancel, 3n minus, that will be, this is equal to 6 Sn. Is it all right? This is equal to 6 Sn. Now what does this give you? This implies 6 Sn is equal to n, 2n square plus 3n plus 1. You split it, 2n square plus 2n plus n plus 1. What is this equal to? N. N into 2n, sorry, 2n, n plus 1, n plus 1. And if you simplify the entire thing, what do you get? If you simplify the entire thing, you will be getting that this becomes n, n plus 1 into 2n plus 1. This is equal to 6 of Sn. So what is Sn is equal to 1 by 6 n, n plus 1 into 2n plus 1. All right. Okay, you know how to add up now n squares of natural numbers. All right. Now I'll request you to do one thing. You prove, take 3-4 minutes, try to prove this. That is 1 cube plus 2 cube plus 3 cube up to n cube. This is equal to 1 by 4 n square n plus 1 whole square. You adopt the strategy as we did in case of squares of natural number. All right. I give you a hint. What you do is you begin with n plus 1 to the power of 4 minus n minus 1 to the power of 4. Okay. You begin with this. R plus 1 to the power of 4 minus r minus 1 to the power of 4. Write the term here and then add left hand side and right hand side. Please do it. Take 3-4 minutes and check that you can do such a thing. Mathematics का है ना? Yes, you are nearing something. Yes, r plus 1 to the power of 4 minus r minus 1 to the power of 4. What is this equal to? Yes, who will tell? What is this equal to? 8r cube plus. Is it equal to this? All right. R plus 1 to the power of 4 minus r minus 1 to the power of 4. This is equal to 8r cube plus 8r. Okay. Once again, what do we do? Put r equal to 1 to up to n minus 1 n. You get what? You'll be getting 2 to the power of 4 minus 0 to the power of 4, that is 8 into 1 cube plus 8 into 1. 3 to the power of 4 minus 1 to the power of 4, that is equal to 8 2 cube plus 8 into 2. 4 to the power of 4 minus 2 to the power of 4, 8 3 cube plus 8 into 3. You continue like that. Last, as we did in the last two lines are, last line is n plus 1 to the power of 4 minus n minus 1 to the power of 4, it is equal to 8n cube plus 8n, and the term prior to that is n to the power of 4 minus n minus 2 to the power of 4, that is equal to 8 into n minus 1 whole cube plus 8 into n minus 1. Is it okay? Add left hand side. If you add left hand side, what do you get? Do you get same? Isn't it? You find that in all the three series we are getting similar expression. And what about the right hand side? Right hand side is 8 1 cube plus 2 cube up to n cube plus 8 1 plus 2. All right. And if you simplify this, what do you get? You will be getting, simplify this, n to the power of 4 plus 4n cube plus 6n square plus 4n plus 1 plus n to the power of 4 minus 1. And right hand side is 8 Sn plus 8. What is the sum of this? We know 1 by 2 n into n plus 1. Okay. Now simplify n to the power of 4 plus n to the power of 4, that will become 2n to the power of 4 plus 4n cube plus 6n square plus 4n, and that is equal to 8 Sn plus 4n square plus 4n. Is it okay? Simplify. What do you get? You will find that 4n gets cancelled. You will be getting 2n to the power of 4 plus 4n cube plus 2n square, that is equal to 8 Sn. Simplify this. What do you get? What about this equal to? You can take 2n square common, n square plus 2n plus 1, that is equal to 8 Sn, and you will be getting what? N square, n plus 1 whole square by 4, that is equal to Sn. All right. So you know how to derive the formula. We use the method of difference. Please go to the next PPT. Skip बात वाली. Next question पे आ जाते हैं. All right. You please try to do this question now. Yes? You mean A? I think that's right. फोर आ जाएगा इसका रेसिप्रोकल लोगे फोर आ जाएगा ना तो आंसर भी 4. Okay, let's look at it. You given that we do not know what is Fn, but it's given that Fn denotes sum of this series. It is some formula which we don't require. What we wish to get is we wish to get r varying from 1 to n 2r minus 1 to the power of 4. All right. Let's write down all the terms explicitly. Okay, let's write down all the terms explicitly. What you're going to get? You're going to get 1 to the power of 4 plus 3 to the power of 4 plus 5 to the power of 4. And you continue like that. What will be the last term? Last term will be 2n minus 1 to the power of 4. And prior to that, it will be 2n minus 3 to the power of 4. Is it okay? This is. Now you see what's missing. You are getting 1, 3, 5. What's missing is 2, 4, 6. Isn't it? So what you have is you can write it as 1 to the power of 4 plus 2 to the power of 4 plus 3 to the power of 4 plus 4 to the power of 4 plus 5 to the power of 4. You continue like that. You will be having here 2n minus 3 to the power of 4 plus 2n minus 2 to the power of 4 plus 2n minus 1 to the power of 4 plus 2n to the power of 4. But what you have added must be subtracted. 2 to the power of 4 plus 4 to the power of 4 plus 6 to the power of 4 up to 2n to the power of 4. Isn't it? What is the term? What is this equal to? F of 2n. You are not bothered what is the formula. You just have to substitute. Instead of n, you put f2n. All right. So you'll be getting that the term within first bracket is nothing but f of 2n. What about the term within the second bracket? What you do is you take 16 common. All right. Can you take 16 common? If you take 16 common, what you're left with? You are left with 16, 1 to the power of 4 plus 2 to the power of 4 plus 3 to the power of 4 up to n to the power of 4. And what is this equal to? This is f of 2n minus 16 f of n. Okay? No problem? All right. Can we have the next one? Okay, you please, you try to do this. Question number 2.
कंसंट्रेट करेंगे, सोल्यूशन तो पुराने हो जाएगा।
Yes. Please see. You got, what you do is you put x is equal to 1 plus 1 by n. All right, you put x is equal to 1 plus 1 by n, so that we don't have to carry two expression, only one expression will have to be carried out. Okay, now what you do is your series now reads like this: 1 plus 2x plus 3x square and It is up to n terms. What is the nth term? Nth term will be what? N into x to the power of n minus 1. Isn't it? And what will be the term prior to that? That will be n minus 1 x to power of n minus 2. Does it look familiar to you? What it is? Arithmetic or geometric progression. What is its sum? You don't remember the formula. All right. So what strategy I told you? I told you a strategy if you don't remember the formula. What was that? What you do is you multiply s by x and shift one term. All right. If you forget the formula, there is no problem. You multiply by x and shift one term. If you do that, what do you get? Look at it. You will be getting x plus 2x square plus 3x cube do you get this? Okay. Subtract. What do you get? If you subtract, you will be getting what? You will be getting 1 minus xs. What is that equal to? 1 plus x square plus x cube x to power of n minus 2 plus x to power of n minus 1 minus n xn. Is it all right? Do you get this? Now, does right hand side look familiar to you? Does it look familiar to you? What it is? It is geometric progression, isn't it? It's geometric progression. At least this part is a geometric progression, and if it's so, what is its sum? Its sum is 1 minus x to the power of n over 1 minus x minus n x to power of n. Is it okay? Does it become this? Check it. Now, what is 1 minus x is equal to? What is 1 minus x? It is minus 1 by n. Isn't it? 1 minus x is minus 1 by n. 1 minus x, it is minus 1 by n. As it is so, you can write it as minus n, 1 minus x to the power of n minus n x to the power of n. Is it okay? What is the left hand side? Left hand side is minus 1 by n into s. All right. Left hand side is minus 1 by n into s. Now look at the right hand side. Is it equal to simply minus n? Okay. Right hand side is simply minus n. So what is s is equal to? Is it equal to n square? All right. It is equal to n square. So your answer is A. All right. Okay, you try to sum it up. Sum to n terms of the series.
क्वेश्चन 2 पे चलो repeat करते हैं।
A request has been received to repeat question number 2. We have to sum up the series 1 plus 2 into 1 plus 1 by n, 3 into 1 plus 1 by n whole square, and so on and so forth, up to n terms. What I suggested was that you put x is equal to 1 plus 1 by n. In that case, your series become s is equal to 1 plus 2x plus 3x square plus 4x cube plus n minus 1 x to power of n minus 2 plus n x to power of n. Now, if you remember the formula for AGP, use it. If you don't remember, don't worry. What you do is, as suggested in an earlier class, you multiply each term by the common ratio, which happens to be x in the present case. You multiply this s by x. Now, this will become x, which I have written here. This will become 2x square, which we have written here. 3x square will become 3x cube, which we have written here. And this n minus 1 x to power of n minus 2, that will become n minus 1 x to power of n minus 1, because we are multiplying by x. It will come here. And this will be multiplied by x, and it will become n x to power of n. Okay. Now, next is, what do? We subtract the second equation from the first. If you subtract the second equation from the first, you will be getting 1 minus x into s. Look at it, s minus x is, that becomes 1 minus x into s. Subtract column wise. First column, let it remain as it is. 2x minus x, that will become x. 3x square minus 2x square, that will become x square. 4x cube minus 3x cube, that will become x cube. And if you do the same thing, it will become xn minus 2. And this minus this will be x to power of n minus 1. And this last expression we write as it is after subtraction, because there is no term in the previous series corresponding to this. So this is what? This is a GP. What is it sum? 1 minus x to power of n over 1 minus x. And this I am keeping as it is. 1 minus x into s is equal to this expression. Now what is 1 minus x is equal to? 1 minus x is minus 1 by n. We put 1 minus x is equal to minus 1 by n. We put 1 minus x is equal to minus 1 by n. It becomes this. All right. Now you simplify this. This is minus 1 by n. So minus n will come in the numerator. Minus n into 1 minus x to power of n. Simplify this. What do you get? This will become minus n plus n x to power of n minus n x to power of n. This cancels. You're left with minus n. Minus 1 by n into s is equal to minus n. So s is equal to n square. All right. Now you please come to this question. I do not know the answer. Okay. What is TR? 1 plus Rx into 1 plus R plus 1x. Is it okay? TR is this. Our strategy. Express it as difference of two terms. How can we do that? Can you express it as difference of two terms? Look at the strategy. What do we do? See, always try to find out what is the difference of these two terms. That is R. No, it is X. Isn't it? The difference of these two terms is X. Okay. Now, if you have the difference of these two terms is X, what you do is you write it as 1 plus R plus 1 X minus 1 plus Rx. Okay. And here you write 1 plus Rx into 1 plus R plus 1 X into 1 by X. Check it. Is it okay? What you do is you look at the difference of the two terms which you have in the denominator, multiply and divide by the difference. Okay. And what is this equal to? This is equal to 1 by X. And if you simplify the entire expression, please see, separate out 1 plus R plus 1X will cancel. You're left with 1 plus Rx minus 1 plus R plus 1X. Is it okay? Do you get this? All right. You have written TR equal to this. If you have written TR equal to this, now what is going to be this? R varying from 1 to N, sigma TR. 1 by X. Here, what will be left? 1 term and the last. Rest of the terms will get cancelled. Isn't it? First term and the last, and rest of the terms will get cancelled. You will be left with what? You will be left with 1 over 1 plus X minus 1 over 1 plus N plus 1 X. Is it okay? You'll be left with these. If you're not comfortable, write the term, write explicitly. Okay. 1 over 1 plus X minus 1 over 1 plus 2X. 1 over 1 plus 2X minus 1 over 1 plus 3X. Continue like that up to N terms and see that alternate terms are getting cancelled. Okay. You are left with 1 over 1 plus X minus 1 over 1 plus N plus 1X. Okay. Simplify. What you're going to get? If you simplify this, you're going to get, it will be 1 N plus 1X minus 1 minus Nx. Sorry, X. Over X into 1 plus X into 1 plus N plus 1 X. Is it okay? What are the things which are going to get cancelled? 1 will get cancelled. This X will cancel with this term. You're left with Nx, which will cancel by X will cancel with X. And your answer will be N over 1 plus X into 1 plus N plus 1X. Is it okay? Your answer will be this. Let's go to the next question. All right, you please try to do this one. A request has been received to repeat question 3. All right. Now, first is, what is rth term? All right. First is you have to write down the rth term. To write down the rth term, what you do is you concentrate on the first expression. It is 1 plus x, 1 plus 2x, 1 plus 3x. That means the first expression in the rth term is going to be 1 plus rx. Okay, the first expression is going to be 1 plus rx. What about the second expression? Second expression is obtained by adding x to the first expression. That means you will be having tr is equal to 1 plus rx into 1 plus r plus 1x. Okay, now we have to express it as difference of two expressions. All right, we have to express it as difference of two expressions. When we have to express it as difference of two expressions, if you can see it immediately, it's okay. Otherwise, we have one strategy. What do we do is, you replace 1 plus rx by a. That is, you rewrite it like this. Okay. What will be the second expression? Second expression will become a plus x. Is it all right? Second expression will become a plus x. Now you write it as a plus x minus a over x into a plus x. Forget this a, let's keep it outside. What about this expression? This will become 1 by x into 1 by a minus 1 over, oh sorry, this should be x. Wait. Okay. And what is this equal to? This is equal to a plus x. All right. 1 over x, 1 over a minus 1 over a plus x. Look at, you put back the value of a as 1 plus rx. You get this. Look at this. Compare the two expressions. Simply replace a by, we have taken this as a. So 1 by x, 1 over 1 plus rx minus 1 over 1 plus r plus 1x. Now, write down the terms explicitly, add them up. You will be left with the first expression 1 over 1 plus x minus 1 over 1 plus n plus 1x. Simplify. You get the answer as, oh sorry, B. Okay. All right, please come to question 4. I do not know the answer. I'll have to see what you've done. Show me. You can pair it and show it to me. Can you write down what is the nth, what is the rth term? First thing which we have to do is we must be able to write down the rth term. All right, let's look at how do we write down the rth term. First term is n square. Second term is n square minus 1 square. Third term is n square minus 2 square. Don't you think that rth term should be this? Rth term should be this. R takes values from 1 to n. Check it. See, let's look at this term. How can you rewrite this? 1 into 2n minus 1. Look at it. So far as this is concerned, can you write it as n minus 1? Can you write this as n plus n minus 1? Last term, express it like this. N minus n minus 1, that will give you this one. N plus n minus 1 will give you the second expression. Okay. So this will become n square minus n minus 1 square. All right. It fits perfectly into this formula. Okay. How do we sum it up? How do we sum it up? We are interested in this sum. All right. Yes. How are you going to sum it up? What will be the sum of this expression? That will be n into n square. Isn't it? That will be n into n square. What about the second one? Second one is, write it explicitly. It is 0 square plus 1 square plus 2 square up to, what is its sum? This is n cube minus 1 by 6 n into n minus 1 into 2n minus 1. Because you're summing up first n minus 1 squares, not n squares. Is it all right? Look at the things carefully. You're summing up 1 square, 2 square up to n minus 1 square. And what is the formula? Formula is 1 by 6 n minus 1 into n into 2n minus 1. When you sum up this much. All right. So what is your answer? None of these. Okay. Your answer is D. None of these. एक मिनट ऐसा करिए, क्वेश्चन 8 पे पहले आ जाइए आप. क्वेश्चन 8. Question 9. Yes, we'll sum up this series. Sum up to 30 terms.
सारे रिपीट होंगे तो कैसे अभी देखते हैं, बाद में देखते हैं.
Yes, first is write down the rth term. That should not be any problem. What about the rth term? Yes, what is rth term? Rth term is 1 over r, r plus 1, r plus 2. Okay. Next, what we should do? we try to write it as difference of two terms. Could you write it? How you have written it?
R into R plus 2 minus R into R plus 1 over R into R plus 1 R plus 2 into 1 by R.
But that will not help. Collapse नहीं करेगी. Yes. 1 over R into R plus 1 into R plus 2. The strategy which I told you will work. That is, you write it as difference of two expressions in the denominator. That will work when you have just two expressions. Not in this case. Maybe you are able to write it, but may or may not help. Okay. Now here is an alternative. That alternative is you try to split it as three terms. All right. 1 over R separately, 1 over R plus 1 separately, 1 over R plus 2 separately. Okay. I've already told you how to do that. We have already discussed it in one problem, how we can do such a thing. Look at it, what I told you. I told you what you do is you write 1 by R plus 1, 1 by R plus 2. You write it like this. Okay. Now you wish to write down what is the coefficient for 1 over R. You set R equal to 0. Hide it. Do you remember? Can you recall what I told you? That is, you set R equal to 0. Hide this expression. And what you're left with? 1 upon 2. Put R equal to 0 everywhere. That is, you will be getting 1 over 2R here. Okay. What is next? You want what is 1 over R plus 1? Set it equal to 0. All right. You set it equal to 0. And this will hide this. Put R equal to minus 1 at rest of the places. You will be getting the coefficient is minus 1. Now you come to this. You set R plus 2 equal to 0. When you put R is equal to minus 2, what do you get? Minus 2 into minus 1, that is this. Okay. Are you clear about it? See, you wish to split three terms separately. That is what we call this as partial fractions. All right. Once again, let's look at what do we do is we have three expressions. We write 1 over R plus 1, 1 over R plus 2. Now we wish to write down the coefficients. To write down the coefficients, what we should do? To write the coefficient of 1 by R, you set R equal to 0, hide it, and put R equal to 0 in rest of the expression. What do you get? You will be getting 1 over 2R. Now you wish to write down what is the coefficient for R plus 1. Set R plus 1 equal to 0. What is that equal to? R is minus 1. You put R equal to minus 1 everywhere except in this expression. You get minus 1 into plus 1, that is minus 1. All right. Next, you take R plus 2. Okay. You take R plus 2. You set R plus 2 equal to 0. What is the value of R? Minus 2. You put R equal to minus 2 everywhere except last expression. You get minus 2 into minus 1, that is 1 by 2. All right. So we have obtained the partial fractions. What is our strategy now? Our strategy is, see, if you try to do it directly, it will become slightly cumbersome. All right. Maybe it becomes very difficult for us to handle the expressions. We now look at how we can make our work simple. What we do is, we first observe that 1 by 2 plus 1 by 2 minus 1, that adds up to 0. Okay. You look at it, I can write it like this: 1 by 2R minus 1 by 2 plus 1 by 2 into 1 over R plus 1. plus 1 by 2 over 1 over r plus 2. All right. Can you write it like this? Check it. What we have done is we have once again split the middle term. All right, we have once again split the middle term. When we have split the middle term, we have combined one part of it with first term, one part with the last expression. All right, we get 1 by 2, 1 over r minus 1 over r plus 1, minus 1 by 2, 1 over r plus 1 minus 1 over r plus 2. Now it is in the form which we desire. Okay, it is in the form which we desire. If it is in the form which we desire, and if I wish to sum it up, what is this equal to? R varying from 1 to n t r. Yes, look at the first one. What does it become? Does it become this? We have to add up to 30 terms, but I'm adding up to n. Then I'll put n equal to 30. Does the first expression add up to this? What about the second one? Second one is 1 by 2, 1 by 2 minus 1 over n plus 2. Is it okay? See, when you add up, if you go to the second term, when you put r equal to 1, you will be getting 1 by 2, then 1 by 2 minus 1 by 3, 1 by 3 minus 1 by 4, 1 by 4 minus 1 by 5, and last will be 1 by n plus 1 minus 1 over n plus 2. All the terms except 1 by 2 and 1 over n plus 2, they will get cancelled out. Okay, and you're left with what? You will be getting here, simplify this, you get n into 2 by n plus 1. Plus, sorry, minus. If you simplify this, n plus 2 minus 2, what do you get? 1 by 2 n. Please make a check. Is it okay? And if I simplify this, what do I get? I'll be getting, you can take n by 2 common, 1 over n plus 1 minus 1 over n plus 2. Is it all right? Do you get this? And if you simplify, what are you going to get? You'll be getting n by 2 into 1 over n plus 1 into n plus 2. Now what you do is you put n is equal to 30 and you get the answer. Okay? You put n equal to 30, you get the answer. All right. Okay. Please see, the question has been asked how to write as difference of two terms. See, our strategy changes from question to question. All right, our strategy is going to change from question to question. That is, somehow we must try to reach a series which will collapse to just two terms. Okay, please see. If you have TR equal to 1 over R, R plus 1 into R plus 2. Let me take first this. 1 over R into R plus 1. In this case, the things are very easy. All right, in this case, the things are very easy. You can write it immediately almost. If you wish to go by the strategy, you go by the strategy like this. You write 1 by r plus 1. Okay, you write 1 by r and 1 by r plus 1, and now adopt the strategy I told you. You set r equal to 0 and then put r equal to 0 everywhere except the first one. What are you going to get? You will, if you do that, what are you going to get? You'll hide it, put r equal to 0, 1 over r. All right. Now, to write down this expression, what is the coefficient for this expression? You set r plus 1 equal to 0. That means you will be getting r is equal to minus 1. You hide it and put r equal to minus 1 everywhere except in that expression. You will be getting minus 1. So, you reach this. Okay, you reach this. And if you have more terms, say we have this. All right, as we were discussing in this question, if we have more terms, then it may not be possible for us to write down as difference of just 2 terms. In that case, we'll try 3 or we may try 4. Okay, we may try 3, we may try 4. For instance, in this case, if you wish to write down, how will you get it? You once again adopt the same strategy. Write 1 over r plus 1, 1 over r plus 2. Okay, do the same thing as I told you. You set r equal to 0 and you hide r, put r equal to 0 everywhere. You will be getting 1 by 2r. Put r equal to minus 1, hide it, put r equal to minus 1 everywhere. You will be getting minus 1. So you get this term. Now you put r equal to minus 2 everywhere except in this term. You will be getting 1 by. Okay. Now what you do is you write it as we told you that you split this. Now you have written it as 2 different collapsing series, telescoping series. All right. You add this separately, this separately. Okay. All right. I'll tell you one more way of doing the same question. All right. Let's look at one more way of doing the same question. See, that is also method of difference. See what you do. You try to connect TR and TR plus 1. All right, try to connect TR and TR plus 1. Please look at it. What you do? You write what is TR plus 1. TR plus 1 is R plus 1 into R plus 2 into R plus 3. Okay. You have TR plus 1 equal to that. What you do is, if you look at the 2 terms carefully, you will find that these 2 expressions, R plus 1 and R plus 2, they are identical in the 2 terms. All right, they are identical in these 2 terms. So what do? We adopt a strategy. What do is we write it RTR, is it equal to R plus 3 TR plus 1? Check it. What I've done, I've shifted this R here, R plus 3 here. Is it okay? Are you getting RTR is equal to R plus 3 into TR plus 1? No problem with that? Okay. if you're getting R TR is equal to R plus 3 into TR plus 1, we can use this relation to do our question. All right. You are not going to learn all the strategies overnight. This you must remember. Okay. Don't panic if you're not getting it when I'm telling you. You'll have to ponder over it. You'll have to think about it. Okay. Nothing comes overnight. Now, somehow, I will try to express my TR or some multiple of TR in terms of these two expressions. All right, let's look at it. See, what do we do? Very simple way is 3TR plus 1, that is equal to please tell me, is it okay? Can you write it as 2TR plus 1, that is equal to RTR minus R plus 1 TR plus 1? No problem with that. Now what you do? You put R equal to 1, 2, 3 up to n minus 1. All right. You put R equal to 1, 2, 3 up to n minus 1. Why n minus 1? That will be clear to you in a minute. What will be left hand side? Left hand side will be 2T2, that's equal to 1T1 minus 2T2. 2T3, that is equal to 2T2 minus 3T3. 2T4, that is equal to you continue like that, you get 2Tn, that is equal to what? That is equal to, yes, n minus 1, Tn minus 1 minus nTn. Check it. Is it all right? Add left hand side and the right hand side. If you add left hand side, what do you get? Add left hand side, you will be getting 2T1 plus T2 up to, sorry, T2. T2, T3 up to Tn. What is that equal to? That is equal to, yes, that is equal to 1T1 minus nTn. Is it all right? That is equal to 1T1 minus nTn. Is that all right? Now, please see. Can you do this? Add 2T1 both the sides. All right, you add 2T1 both the sides. If you add 2T1 both the sides, you will be getting twice of T1 plus T2 plus Tn, that is equal to 3T1 minus nTn. And what is that equal to? What is 3T1? 3T1 is, yes, is it 1 into 2? What is nTn? That is n plus 1 into n plus 2. All right. You can divide by 2, you get the answer. But as I've already said, that you're not going to learn all the techniques overnight. It will take time. Okay, it will take time. So don't worry. If you understand it, okay, think about it at your home. All right. Otherwise, you have the alternative. All right. Otherwise, you have alternative strategy, splitting it into partial fractions. Okay. Using this, let's come to question number. कौन सा question छूट गया था? All right. एक मिनट. इसके बाद question number 7 पे आ जाइए. Yes. Try this. First, try to write down what is rth term. It's similar to the previous problem.
not end up to doing this. To write those.
Yes. All right. What is the rth term? What is TR? TR is 2R minus 1 R plus 1 into R plus 2. Okay. Is that all right? No problem with that? All of you have written rth term. Now, once again, our strategy will be split it into partial fractions. Okay, split it into partial fractions. Now, for splitting into partial fractions, we adopt the same method which we adopted in the previous question. 1 by R plus 1, 1 by R plus 2. Okay, you put R equal to 0. All right, you put R equal to 0. And then what you do is, you put R equal to 0 everywhere except here. What do you get? Yes, tell me. Do you get minus 1 by 2? Check it. Is it all right? When you put R is equal to 0 everywhere except there, you will be getting minus 1 by 2R. All right. Next, you put R equal to minus 1 everywhere except in this expression. What do you get? Yes, tell me what do you get? 3. All right. Minus 1 by 2R. Let me write it here. Oh, okay. You please go to the last thing. You put R is equal to minus 2 everywhere except in the last part. What do you get? Minus 5 by 2. Okay, that done. All right. Now you please see that once again what you have to do is that you just add up the coefficients. Minus 1 by 2, minus 5 by 2, plus 3. What is the sum? Is it 0? Minus 1 by 2, minus 5 by 2, plus 3. This adds up to 0. Okay. Now look at it, what I do. I'll be splitting this 3. I'll write it as 1 by 2 plus 5 by 2. Okay. Let's write that 3 as 1 by 2 plus 5 by 2 and rewrite the entire expression like this. Check it. You're comfortable with this? All right. Please see what you have to do. Split the middle term again. Combine part of it, the requisite part with the first expression and requisite part with the second expression. Okay. You get here minus 1 by 2, 1 over R minus 1 over R plus 1 plus 5 by 2, 1 over R plus 1 minus 1 over R plus 2. Now, this is your TR. Is it okay? This is your TR. What will be the sum? Sigma TR is going to be, yes, tell me, what is it going to be? Minus 1 by 2 as it is, first term minus last term. Okay. Minus 1 by 2, 1 minus 1 over n plus 1. Plus 5 by 2, 1 by 2 minus 1 over n plus 2. All right. Now you add them up. What do you get? Yes. You get here. If you simplify this, you will be getting what? N plus 1 minus 1. That is n. That is minus n over 2 times n plus 1. Does it simplify to this? What about the second one? Plus, let's check up the answer. What do we want? All right. Okay, plus 5 by 2 into 1 by 2 n over n plus 2. Is it all right? Shall I leave the remaining simplification for you people? I leave the remaining simplification for you people. Only thing which is to be done is you take n by 2 common from both the expressions, simplify. All right. Okay. Please see. Because I'm telling you a method, I must tell you where you should not use it. Say for instance, instead of your rth term is 2r minus 1 r over r plus 1 whole square into r plus 2. Let's say this. Okay. Then the method I have told you is not going to work. There is a separate method which I cannot go right now. All right. I cannot discuss that method right now. Okay. That perhaps you may discuss sometimes in class 12. All right. So please remember that it's not going to work in this case. Secondly, please see, whenever you're writing like this, you must remember that whenever you have a linear expression here, you must have a constant in the numerator. All right. The degree of difference between the numerator and denominator must be at least 1. Okay. So you cannot do like this that all right, I can express it like this, r over r plus 1. No, that's not going to help. Okay. The difference between the degree in the denominator and the numerator should be at least 1. Okay. No problem. Next question. All right, you please try this question. Then I'll. Oh, there is someone has requested that this question be repeated. Yes, you write down what is the rth term. Is the rth term clear to all of you? Rth term is 2r minus 1 over r into r plus 1 over r plus 2. Okay. Now, we shall rewrite this splitting into partial fraction. Write 1 by r plus 1, 1 over r plus 2. Okay. Now, let's try to find out what are the coefficients of 1 by r plus 1 and 1 by r plus 2. Same strategy, you put r equal to 0 everywhere except here. You'll be getting what? Minus 1 over 2. So this is going to be minus 1 by 2r. All right. Next, you put r is equal to minus 1 everywhere except in this part. When you do that, you will be getting minus 3. All right. You will be getting minus 3 here. And what will be the denominator? Denominator will be minus 1 into 1. That will be plus 3. Next, you put r equal to -2 everywhere except in this part. You put r is equal to -2. You get -5 over 2. So this is plus 5 by 2. All right. Now merge in an appropriate manner. That is what you do is this 3 will be split as 1 by 2 plus 5 by 2. So that this part can be combined with this and this part can be combined with this. And this will become minus 1 by 2, 1 over r minus 1 over r plus 1 plus 5 by 2. This should be negative. This is negative, sorry. 5 by 2, 1 over r plus 1 minus 1 over r plus 2. Now what you do is you deal with this expression separately, this expression separately. This is TR. Okay, what is this equal to? This is, it will collapse to what? 1 minus 1 over n plus 1, and this will add up to 5 by 2, 1 by 2 minus 1 over n plus 2. All right. Now simplify this expression. Minus n by 2 into n plus 1 plus 5 by 2 n plus 2 minus 2, that will be n by n plus 2 into 1 by 2. Now what you do is you can take n by 2 common. If you take n by 2 common, what you're going to get? You'll be left with what? This n by 2 is taken common. 5 by 2 into 1 over n plus 2 minus 1 over n plus 1. That can be simplified. I'll leave the simplification for you. All right, that can be simplified and you'll get the requisite answer. All right, let's go to the next question, please. Try, please, this one. Yes, we've already done a similar question. I do not know the answer. Maybe. Just tell me how you've done. Very good.
And this y into n and this form of zero was an
Your answer is A. See, that's a very simple question. What you do is, last time, I think yesterday we discussed a similar problem. You got 3 by 2 plus 5 by 4 plus 9 by 8 plus 17 by 16, and you continue like that. Write it as 1 plus 1 by 2. This is okay. You write it like this. Now 1 1 1 that will occur n times, and the other series will sum up to 1 by 2 into 1 minus 1 by 2 to power of n over 1 minus 1 by 2. So if you simplify this, you will be getting n. This 1 by 2 and this 1 by 2 will get cancelled, plus. All right. This okay. Question 10. All right. Let's see how we do this. Let's first try to understand the question. The question is sum of all the terms in the nth row of the triangle. See, what you do is you're doing is you're writing the natural numbers like a triangle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it will be 11, 12, 13, 14, 15, like that. What we wish to do is we wish to find out what is going to be the sum of the terms in the nth row of this triangle. Okay, try. Think how you will do it. Second, B. How did you reach it? Verify कर लिया. I'll be careful next time so that you don't verify. Tell me how you will get the answer. You put n is equal to 1. अच्छा. Yes. Anything you can think of? All right, we'll see. We have this question. Let's try to look at what information we can extract out of it. First row contain how many natural numbers? Second, 2, third, 3, fourth, 4. That means first thing which we notice that nth row is going to contain n numbers. But the problem is that we do not know what is the first number. If we know what is the first number, the nth row, no problem. We can immediately write down its sum because we know the common difference and it's an arithmetic progression, isn't it? And we also do not know what is the last number. Even if we know the last number, I can go backward, isn't it? But if I know what is 100, I can, if I wish to add up 199, I know that it's an arithmetic progression whose first term is this and the common difference is -1. All right. That means one strategy is that somehow either we try to get the first term of the nth row or the last term of the nth row. Okay. Now, I tell you that it's very easy to get last term of the nth row. All right. It's very easy to get what is the last term of the nth row. Yes, what is the last term of the nth row? Okay, let's presume that we are not able to get it. Okay, then I tell you what strategy we are going to adopt. If you cannot write down what is the last term of the nth row, don't worry. What we do is we say that let's concentrate on the last element of the each row. First is 1, 3, then 6, 10. You continue like that. Last term we do not know, write it as Tn. All right. And the term prior to that is Tn minus 1. Okay. Now, one strategy is method of difference. That is, you rewrite as, but with one term shifted. Okay. Take the difference. If you take the difference of s with s, what is left hand side? 0. Right hand side, 1 plus 2 plus 3 plus 4. Is it okay? So, what is Tn? Is it all right? You have obtained what is the last term of the nth row. Verify. If you take n is equal to 1, what is, do you get 1? If you put n is equal to 2, do you get 3? If you put n is equal to 3, do you get 6? Is it all right? That means nth last term of the nth row is 1 by 2 n into n plus 1. But we did not require this. We did not require doing all this. Why? Because you know that first term contains one element, second contains two elements, third contains three elements, fourth contains four elements. Add them up. How many elements are there? Isn't it? Like that you could have done. Anyway, we know what is the last term. Let's forget everything else. Okay, can you now write down what is the sum of the last row? Yes. What is the sum of the last row? This is your A. D is minus 1. Number of terms is n. So it is going to be n by 2, 2A plus n minus 1D. Okay. And what is that equal to? What is 2A? It is n into n plus 1. What is D? Minus 1 minus n minus 1. Oh, sorry, plus 1. Is it all right? So what is your answer? 1 by 2 n into n square plus 1. All right. 1 by 2 n into n square plus 1. D. Is that okay? No problem with this? We could have obtained this in an alternative way also. Okay. Let's try. Let's find out what is the sum of all the terms up to the nth term. All right. Let's find out all sum of all the terms up to the nth term. What is sum of all the terms up to the nth term? Can you find out? Very simple. You know, you have to find out sum up to this, isn't it? That is, you treat it as m, and what is sum of all the terms up to nth term? That is going to be, let's put it as say tn. That is going to be 1 by 2, 1 plus 1 by 2 n into n plus 1. That is the sum of all the terms. Sorry. Rather 4. Okay. Sum of all the terms up to nth term is this much. We have obtained sum of all the terms up to n row. What will be the sum of all the terms up to n minus 1 row? Replace this by n minus 1. N by n minus 1. Subtract. You get the answer. Is it okay? No problem? All right. You may think about this question once again at your home. Let's take a problem which is given you in the material that has been distributed to you by Udaan. That question is, you have to find the sum of this series. Up to infinite. Question number 10. Abhi karte hain. Why would to take क्वेश्चन नहीं आ रहा. And now, before we go to this question, the question has been asked, why were we to take d equal to -1? Please see, you have obtained the sum up to the last term. Let's look at the fourth term. We have obtained the last term. And if we go backwards, then the common difference will be -1. That's why we are taking as -1. Okay, 10, 9, 8, 7. That is, the difference is -1. So if we have written the last term of the nth row and going backward, it is an AP with common difference -1. All right, उसको छोड़ दो, ये वाला डिस्प्ले कर. How much time? 10 minutes. क्योंकि एक क्वेश्चन और डिस्कस करना इसके बाद. Yes. First is, what is rth term? Yes, rth term is TR is 1 over r plus 2 whole square, very good, plus r. Okay, simplify this, what do you get? R square plus 4r plus 4 plus r, that will become r square plus 5r plus 4, and that you can rewrite as, yes, can you write it like this? Split it into linear factors. Okay, if you split r square plus 5r plus 4 into linear factors, you'll be getting, it becomes r plus 1 into r plus 4. Okay, can you write it as difference of two terms now? Write it as difference of two terms. Yes, what is difference of two terms now? You recall the strategy, r plus 1, 1 over r plus 4, put r is equal to minus 1, 1 by 3, put r is equal to minus 4. All right, this is the way you can do it. Otherwise, think of the difference. That is what? 3. Write it as, okay, and separate out. All right. So we know this. We have to add up to infinity. Let's do that. We add first term, that will be 1 by 2 minus 1 by 5 plus 1 by 3 minus 1 by 6 plus, what will be that? 1 by 4 minus 1 by 7. Next, 1 by 5 minus 1 by 8. All right, you continue writing like this up to infinity. Okay, what is this equal to? Yes, please see that 1 by 5 will get cancelled. Next term will cancel 1 by 6, 1 by 7. All the terms, because you're going up to infinity, all the terms will get cancelled except the first 3. Is it all right? That is, you'll be left with 1 by 2, 1 by 3, 1 by 4. So you're going to get S is equal to 1 by 3 plus 1 by 2 plus 1 by 3 plus 1 by 4. Add them up, what do you get? What do you get? Yes, 13 over 24. 13 by 12. All right. So your answer is 13 by 36. Is it okay? All right. We have one question number 3. इससे वापस चलिए आप जरा. अच्छा चलिए इसी को डिस्कस कर लेते हैं. Question 11. 2-3 minutes रह गए ना. I'm sorry, we'll run out of time, so let's discuss it. You given that sum to n terms of an arithmetic progression is Cn square, and you wish to find out what is sum of the squares of the n terms. That is, see, what you do is look at it. You given that T1 Sn equal to T1 plus T2 plus T3 up to Tn minus 1 plus Tn. What is that is given to you? That's given to you as Cn square, isn't it? What you are interested in? You are interested in T1 square, T2 square, T3 square up to Tn square. Is it all right? That means somehow we must be able to find out what is TR. Isn't it? Somehow RT and RTR one and the same thing. Can you see what is Tn is equal to? Is Tn equal to Sn minus 1? Is it all right? Tn is equal to Sn minus 1. And what is that? That is equal to Cn square minus Cn minus 1 square. That is equal to what? C n square minus n minus 1 square. That is equal to C times 2n minus 1. All right. That means we have obtained what is Tn. Is it all right? We have obtained what is Tn. So what is T1 square plus T2 square up to T3 square? Is it equal to k varying from 1 to n tk square? And let's substitute what is tk square is equal to, that is k varying from 1 to n. Tk square is what? C square into 2k minus 1 whole square. Is it all right? And what is that equal to? You can take c square common, k varying from 1 to n, 4k square minus 4k plus 1. Is it all right? And what is that equal to? Yes. What is that equal to? This is equal to c square. Yes. This is 4 by 6 n plus 1 into 2n plus 1 minus 4 by 2 n into n plus 1 plus n. Okay. Shall I leave the simplification for you? And thank you so much because my time is up. Thank you.
Okay, good afternoon, everyone. All right, as you've already started with chemical bonding, we'll just quickly see what you have done till now and simultaneously go ahead and start revising and take up the topics that you haven't taken at all. What you are doing presently is chemical bonding. In chemical bonding, why do we study bonding? Because keep on seeing solids around you. There are very many types of solids around you. What are those types of solids? You have ionic solids, you have covalent solids, you have metallic solids, and you have molecular solids. Just remember, these are the types of solids that you see around yourself, uh, depending upon the kind of bonds that are there in it. You have studied different types of bonds. So now these types of bonds are the ones which constitute different types of solids. And those are like when you were talking about the ionic solids, as the name suggests, what type of bonds will be there in ionic solids? You will have only ionic bonds. All right. Now you know ionic bonds are the ones which are formed by the complete transfer of electrons. All this is something that you have done before. So when we talk about the transfer of electrons, here in this case, you have to make it a point to understand that it is an interaction of an electropositive element with an electronegative element. All right. It is the interaction of necessarily an electropositive atom with an electronegative atom. Okay. One thing that is asked many a times in the examination is that these ionic bonds are non-directional in nature. All right. And you understand the meaning of non-directional? That irrespective of the position from where your anion is approaching, your cation can actually take the attack from any position. Right? It is not dependent upon direction. So next we talk about the covalent bond, covalent solids. Covalent solids are the ones which will be formed with the help of only covalent bonds, and you know that covalent bonds are the ones which are formed by sharing of electrons. All right, primarily by sharing of electrons. And here in this case, you generally see that in covalent solids, you have one electronegative atom with another electronegative atom. So you have the interaction of an electronegative atom with another electronegative atom. Then we have metallic solids. Now you have talked of ionic bonds and covalent bonds. When we talk about the metallic solids, these are the interactions generally between two electropositive atoms. Okay, so just like this, here you have the interaction between an electropositive atom with another electropositive atom. Okay, so these are the ones which form the metallic solids. Metallic solids are generally the ones in which your metal is assumed to be a cation held together by a sea of electrons, and that sea of electrons is known as the Fermi sea. All right. And in the end, we talk about the molecular solids. These are the ones which are held together by van der Waals forces of attraction. These are held together by van der Waals forces of attraction. All right, when we talk about van der Waals forces of attraction, what do you understand? Are these equivalent to London dispersion forces? No. You have very many forces which are in together totaling up to your van der Waals forces. What are those? Iron, iron dipole, 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 and then you have your London dispersion forces. So basically you have your iron dipole, you have your dipole, dipole, and in fact you have your dipole induced dipole forces also, along with your London dispersion forces, which are the general forces of attraction which hold your bonds together. Out of these, when you talk of a dipole, let me throw some light on a dipole. You understand what a dipole is? A dipole is generally a small constitution. It is like equal and opposite charges separated by a small distance. And you know that your dipole moment is generally given by what formula? It is charge into distance. What are the units of dipole moment when you talk about? This is like measured in terms of dipole moment. And what are the units? Either you talk of in terms of coulomb meter, or you talk in terms of ESU centimeter, right? And or you talk in terms of dBi. All right, you know the conversion of one into another. What is it? 1 dB is equal to 1 dB is equal to 1 into 10 to the power minus 18 ESU centimeter, which is also equal to 3.3 into 10 to the power minus 30 coulomb meter, right? And using this, you can actually measure out your dipole moment. Now, why are you studying dipole moment? Dipole moment is something that is always pointing towards your more electronegative atom. Okay, from here I have moved on to dipole, but initially when I talk of dipole, it is nothing but a constitution of equal and opposite charges separated by a small distance. So if that is the case, whenever I talk of hydrogen bonding also, I am talking right initially, whenever I talk of hydrogen bonding forces or hydrogen bonds, what are they? They are between an electropositive hydrogen atom with an electronegative atom, always, right? Say if you have an HCl interacting with another HCl, what is it? It is some kind of a dipole induced dipole, sorry, dipole only, right? You will have your H interacting with Cl. This is hydrogen, this is what is hydrogen bonding all about. So what we can say is that hydrogen bonding is a special case of dipole interaction only, but we do not club it under this heading because the magnitudes or the energies, the bond energies are so different that we take them as a separate class. So always remember that your hydrogen bonding is also a special class of dipole interactions only. Then when I'm talking about the dipole moment back again, which is nothing but charge into distance, what are the basic applications? Why am I studying dipole moment in the first place? You have already done it. Dipole moment is what? Can tell you about the extent of polarity of the bond. It can tell you about the extent of polarity. Greater the dipole moment, greater will be the polarity in your bond. Then the next thing that it can help you is in finding out the percentage ionic character. This is also something that you have done. What is your percentage ionic character? What you do is you take your say observed dipole moment upon the calculated dipole moment into 100, and that will give you the percentage ionic character in your compound. Now this is something that you have already done, so it's a quick revision for all of you all. When I'm talking about ionic solids and covalent solids, what we have stated primarily, a new thing for you is that the ionic solids are non-directional in nature, but your covalent solids will now be directional in nature because there the bonds are set together at a particular angle in order to have minimum repulsions, right? So then thereafter, you have already discussed the phenomenon of resonance, which is like an important phenomena, primarily because it leads to the stabilization of these structures. When I talk about resonance, it leads to the stabilization of these structures. How? Say, this is nothing but resonance is a kind of phenomena which gives you similar structures that contain same number of electrons, all right, and with almost equivalent energies. But how to understand the phenomena of resonance? You know that, you know how to draw Lewis structures and all that, you've already done. Say if I am talking about an H and an H bond, if I talk about an H2 molecule, there is a bond between the two, okay? Now you know that there is a formation of cation and ion, there is a formation of radicals also. How is that happening? When you have the entire bond shifting towards an atom, you have one electron here, so a bond pair of electron. It's a pair of electron. So when I'm shifting this entire bond to an atom, you can clearly see here that this bond is shifting. So that means this hydrogen is giving and this is taking. So this will lead to the formation of H plus and H minus. Clear? Now if I talk about the same bond again, and I know that it is again a bond pair because I have a bond which contains a pair of electrons, and I shift it one electron here and one electron here. So that means I'm not completely shifting the bond. I'm making it halfway this way and halfway the other way. So then in that case, it is yielding my H radicals. Do you understand the difference between the two? I repeat it again. Always remember that a bond is always directed towards an atom, with the help of which the one that gives attains a positive charge and the one that takes attains a negative charge. And if at all a radical formation is happening, how does that happen? In the radical formation, you have half the bond getting transferred on either of the atoms on the adjacent sides of the bonds. So you have half the bond transferring here, that gives 1 electron to this, and the half the bond transferring here means 1 electron to this. So this is leading to the formation of radicals, and I hope you all know that the radicals are highly reactive. Okay, all radicals are highly reactive. They do not remain in the stable situation at all. The moment the two radicals come in touch with one another, they immediately form a bond and leads to stabilization. Just remember that. Then to start with the resonance stabilized structures, you have to understand that whatever structures or the canonical forms that I have, all of them should have equal energies. So if I have to draw the resonance stabilized structure of, say, benzene, you know benzene. So it is this. It has 6 carbon atoms with alternate double bonds. And you know that. Why? Because carbon has a valency of 4. So it should have 4 bonds around it. 1, 2, 3, and the fourth one is hydrogen. Similarly, you have here and here all the carbons satisfying the valency of 4. So this is for you to understand that this is the structure of benzene. Now, when I talk of the resonance stabilization in this case, you should be able to get it for yourself that I am drawing the structure like this. Just carefully look. I know that my bond can shift towards an atom. And where are my atoms? At the corners of this benzene. So how will I begin? I'll shift. This is a double bond. So I can start shifting one of my double bonds. So this double bond comes here to this carbon atom. Clear? So now because this double bond is shifting to this carbon atom, this carbon will get a positive charge and this which has taken will get a negative charge. So the next structure in line would be, you have this is positive, this negative. So this will be the next structure, right? Now again here, my negative charge has a pair of electrons because the entire bond has shifted. See, when the entire bond is shifting, it is getting a negative charge, whichever atom. Here in this case, my carbon is got. So that means it is holding a pair of electrons, which is capable of forming a bond. So this carbon will give, just look here, this now negative charge is getting shifted to the middle of now to the bond to form a bond. Now if this forms a bond, this carbon will now get a positive charge. So positive, negative cancel, neutral. What about this carbon? This carbon, you know, already has a hydrogen atom, right? So if it forms a bond here, it will be 1, 2, 3, 4, and 5. Can carbon have a valency of 5? No. So then in that case, I need to be shifting another bond towards the next carbon atom. Clear? I repeat it again. Here you know that now this negative charge has a pair of electrons which will be directed towards a bond. All right? And now this will form a double bond here. So this carbon gets a negative charge. But this carbon, even after getting a negative charge, is having a valency of greater than 4, which is not possible. So it should be shifting the next bond here. Now this got a negative charge because it got a bond here. From here it is giving, so negative, positive, cancel, it becomes neutral. And then this carbon gets a negative charge here because the bond is shifting towards this carbon atom. So in this case, it becomes, see, we did not touch this positive charge at all. This positive charge is where it was. Then we got the double bond here. Now this negative charge has come here on this carbon atom, and this double bond is something that we did not touch at all. Right? This is the next structure. Clear to everyone? Now let us try the next structure. Here in this case, what we have is this negative charge is again going towards the bond. Same thing happening again. You know it's a pair, so it can form a bond. So this negative charge going towards a bond. This bond going towards this atom. Right? Why? Because again, this carbon, we do not want it to have a valency of more than 4. So here in this case, the next structure therefore will be, you have the positive charge here. Then you have, say, negative. Now this has formed a bond. So we get a double bond here. So this carbon atom has now given, so it becomes neutral because it was negative, it has now given, so positive. This carbon has taken from one side, given to the other side, so no charge on it. And then this carbon has taken up the bond pair, so here it becomes negative like this, right? And then now again, this negative charge is forming a bond in between these two carbon atoms. This carbon will now take up, so it becomes negative, so that means neutral. This carbon has now given, so it becomes again positive, so it becomes neutral. And the resultant form that we get is, you have one double bond here, another here, and the third one here. So if you check it for yourself, now there is alternating, you have the structures representing alternating double bonds. Clear to everyone? Always remember that a bond is directed towards an atom, and an atom is from an atom the charge is directed to form a bond. If this is clear, now remember that here all these resonating structures have equivalent energies. They are known as the canonical forms also. And in general, you represent your benzene ring as this also. That is because it says that there is delocalization of the electron charge density throughout the benzene molecule. Clear to everyone? If this is clear, try it out for chlorobenzene now. Try out the resonating structures for chlorobenzene. And in case of chlorobenzene, what will you have now? Say this is the benzene. Say these are the bonds that we have for benzene. You will have, instead of now a hydrogen, you know that it is C6H6. Now in chlorobenzene, instead of one hydrogen, you have a chlorine here. All right. And you know chlorine has how many valence electrons? 7. So that means 1, 2, 3, 4, 5, 6, and the 7th one is forming a bond. So instead of H now you have 1. So your benzene is C6H6. When you are replacing one hydrogen with chlorine, it becomes C6H5 and Cl. All right. Now I'm asking you to make the resonating or the resonance stabilized structure for chlorobenzene. How will you start with? It has a lone pair of electrons. So instead of starting with the bonds, I can start right away from here. And it is known to have a plus I inductive, it is known to be electron releasing in nature when on top of the benzene ring. So it shows a plus I inductive effect, and it will be like this. One pair of electrons forming a bond in this fashion. Okay. What about the next one? Bond will be directed towards an atom. So here in this case, your bond will be directed towards this atom. Clear? Pair towards towards a bond, forming a bond. So this Cl will now get a positive charge because it has given, right? And this carbon, because now this carbon, if it has double bonds together on either side, it will be 1 Cl. You have 1, 2, 3, 4, and 5. We do not want that, so immediately there is a shifting of the other double bond. So here now this carbon gains a negative charge. So the next structure in line will be, look carefully, now Cl has formed a bond, so it will be this, Cl getting a positive charge. We have not touched the other 2 bonds, so let them be as it is. And now this bond is directed towards an atom, so it will be a negative charge here. Okay. So now here, what you have is, this negative charge will now be forming a bond here. Now the same thing as you have done for benzene, and this double bond will be forming a bond here. Please join, all these structures are joined. So go ahead and draw the rest of the structures. So what will be the next? Here the next structure will be, you will have Cl positive. Now this negative charge is forming a double bond here. This double bond is shifting, so this carbon gets a negative charge, and then you have this double bond which we haven't touched, the rest of the molecule remains as such. What about the next case? The negative charge forming a bond in the next case, and this double bond will again shift towards an atom. So your positioning or the arrow should be absolutely crystal clear that the arrow from a bond is going towards an atom, and from an atom it is going towards the formation of a bond. You should not just draw it like this and leave it in the air. It is absolutely wrong. Clear to everyone? From a bond towards an atom, and from an atom it will go towards a bond. So this charge going towards this forms a double bond. This double bond is now going towards the atom. So what will be the next? The next structure, look carefully. We haven't touched this bond now. All right. We have formed a double bond here. We have got a negative charge here. Cl positive as it is. Okay. And then for the next, we can have for the next, what is going to happen now? This negative charge will again form a bond. The negative charge will be directed towards a bond to form a bond. And again, this carbon will now have two double bonds on either side. So let's check the valency. It will be 1, 2 when the bond will be formed, 3, 4, and 5. So that means we need to shift the next double bond again. So it will come towards this atom from where we initially started. So it will be, you will have these two double bonds as such. We have another double bond here and Cl. Cl was positive, so it has now taken up a bond, so it becomes negative, so it becomes neutral. Finally, and this is, now again if you check this structure and this structure, there is alternation of the bonds, right? Initially the bonds were here, now the bonds have shifted to the alternate position. So again, for the general structure of chlorobenzene, it also can be represented like this. That is how. And because of the electron donating capabilities, you see that here itself, just if you have, or if you will be doing it inorganic as such. So here, just pay attention. Here you get one more information from the resonance stabilized structures. As you were creating the resonance stabilized structures, look carefully that you have the negative charge here, and then you have the negative charge here. You know that this is the ortho position, meta position, para position. So you see that the negative charges are there at ortho and para. So these are the positions where this is ortho, this is para, again at ortho. So you see that these are the positions where your electrophile will attack. You will be studying it in organic also, that your chloro group is it's ortho para directing for an electrophile. So you get an idea. See, if you have the negative charge at this position, that means a positive charge can come here and attack. Right? Again, while you check the resonance stabilized structures, you see that the negative charge also is here. So all these positions are electron rich. Got the point? Why electron rich? Because basically it is an electron pair which is shifting towards this atom. And then this negative charge is holding the pair of electrons. So wherever you find that the electron pair is concentrating, those are the atoms where your positive charge can come and attack. Got the point? So is the case with benzene also. When we did benzene, there is an equal probability of all the charges to come at any position because all the hydrogen atoms are equivalent. But once you get an atom on top of benzene, they are demarcated as ortho, meta and para positions depending upon their positions from that particular functional group which is attached. Clear to you? Okay. Now from here we get information that each structure in resonance should be such that the position of the atoms is not altered. So you see that we have not altered any of the position of the atoms. Next important key feature of resonance is that its structure must have same number of unpaired electrons. Same number of unpaired electrons means structures must have same number of unpaired electrons. For this, if we take up an example of say NO, we have N here. All right. So the equivalent structure for this NO can be you can have this along with this. With this will not be allowed. If you draw something like this, say this, then this kind of a structure is not allowed. So the number of unpaired electrons also should remain the same. You have one unpaired electron, so the number of unpaired electrons should always look like 1 in the resonance stabilized structures whenever you are drawing. Then those structures in which the negative charge resides on the electronegative atom and the positive charge remains on the electropositive atoms are closest to the actual geometry. And for this, we can show that say if you consider the example of HCl, just a random example, whenever, if I want to have canonical structures, remember that you can have resonance stabilized structures if you have any position of the bond which can be shifted. So here in this case, if I draw say a resonance stabilized structure for this as this, so there will be one possibility that you will have H plus and this will be Cl minus. This is one possibility. Otherwise, there is another possibility. This is a bond which is unbiased. You can have the shifting of the bond towards the hydrogen also. Then in that case, what would be the other form? It will be H minus because now the bond has shifted towards hydrogen and it will be Cl plus. So what the third rule of resonance states is that whenever you have the positive charge on the electropositive atom and the negative charge on the electronegative atom, then that structure is the closest to the actual structure than the other structure. So that will have a different energy. All right. But then equivalent energies in all these cases if you are shifting the bond. Clear to everyone? So I repeat it again that whenever you have the positive charge on the electropositive atom and the negative charge on the electronegative atom, then that structure is closest to the true structure. So here, when you talk of a general HCl bond, you know that this is Cl is like this. So when you draw this, this is what? This is a covalent bond, right? Whereas in this case, this is the ionic and this is also the ionic bond which can be formed using this structure, right? Whenever you talk of ionicity, that means you're talking about separation of charges also. So here when you're talking about ionic, this is ionic, this is ionic, this is covalent, but which one of them would be acceptable more? This one. Clear? Next, we have another rule which states that the contributing structure should be so written that the unlike charges must reside generally on the neighboring atoms. In some of the cases, the unlike charges should be arranged in such a fashion that they are on the adjacent atoms. Like for example, if you take the example of HN3, all right, then that will be, you have a positive charge here, you have a negative charge here. It is generally written as you have now say a lone pair of electrons here. So why does nitrogen have a positive charge here? This is attributed to your coordinate covalent bonds. You know about coordinate covalent bonds? These are formed by the bonding from the lone pair which is situated on one of the atoms. Like for example, if you have NH3, you know that the valency of nitrogen is 3. What is nitrogen? The atomic number is 7. So it is 1s2, 2s2, 2p3. You know that the valency of nitrogen is 3. So it should be forming 3 bonds around it. And it has a lone pair of electrons contained in the S. So you will have the lone pair here. This lone pair, when it forms a bond with another atom, then you say that it's forming a coordinate covalent bond. Say it can accommodate another H here with this bond. So there is only one pair of electrons between the two that you have to understand, and this nitrogen will now develop a positive charge. So remember, whenever nitrogen, because the valency of nitrogen is 4, what we have is Because of this, sorry, the valency of nitrogen is 3. Whenever we have an extra bond getting formed, this bond will make nitrogen develop a positive charge on it. And this goes true for oxygen as well. For oxygen, you know, it is like 2 pair of electrons. And what is the valency of oxygen? It is 2. So you have oxygen as this, along with 2 hydrogen atoms. This is your water molecule. And when you see that a lone pair is now, this is accommodating another bond, say with H, because of the lone pair situated on it, what will now oxygen develop? A positive charge. So whenever you add H plus to water, it accommodates that H plus with itself to form H3O plus. You get the point? So whenever those atoms which have the capability of forming a coordinate covalent bond will immediately develop a positive charge because of their lone pair which is available on their top. All right. Now coming back to this example that I was talking about, HN3. Here you see again this negative charge will be directed towards a bond, and a bond will always be directed towards an atom. This should be clear. So here you will now have a negative charge here, right? And then this will be positive because it has taken from one side, given to the other side, so the charge remains as such. And this will be N. And another form can be when you have the shifting of the bonds from the other side. And always remember that greater the number of covalent bonds, greater is the contribution of the resonating structure also. Now we can take up some examples for resonance. See, one example can be that of carbon monoxide. You have carbon monoxide having this kind of a structure. So if this gives, what is the alternating the other structure? It will be this carbon is accepting and this becomes carbon monoxide. And so goes with the other case also. Now in this case, if you have, because you know oxygen is electronegative in nature, all right, so it can even take up this bond pair on itself. So then in that case, it would be C positive, O negative. So you can try the next example of carbon dioxide also. This is your carbon dioxide structure. This is your carbon dioxide. Now here, I repeat for the carbon monoxide case, you know that a lone pair can get shifted towards a bond and a bond can get shifted towards an atom. So here when you see that the lone pair is shifting towards a bond because this oxygen is giving, so it develops a positive charge. It forms a triple bond here and then it is a negative charge. Now here again, when your bond is shifting towards, why am I shifting the bond only towards this? Because you know generally your oxygen is electronegative in nature. Electronegative means it is the tendency to accept electrons. So here in this case, I'm shifting this bonds towards oxygen, so it develops a negative charge. And because this carbon has now allowed the shifting of the bond, so it is like of giving nature, so it will develop a positive charge here. Clear? Now for carbon dioxide again, you can actually try it out. You will have 2 lone pairs here. So I don't want the valency of my carbon to exceed, so the other structure would be this. Now you understand from the have you understood benzene completely? Now it is just like that. You have a lone pair which is readily available to form a bond. It has shifted towards the bond now, but then if it has shifted, this oxygen will now develop a positive charge because it has given. And this carbon has taken from one side, but if it takes triple bond here and double bond here, again the valency will now be more than 4. That is again not possible. So it will now be C triple bond O. I don't want the valency to exceed, so this bond will shift ahead towards oxygen, which is a possibility. So this oxygen will now develop a negative charge, and because this oxygen is given, it will develop a positive charge. And as I told you, for the coordinate bonds, what we have is, for the coordinate bonds, what do we have? Oxygen is generally having a valency of 2. The moment it uses the third bond, it will develop a positive charge, right? This is what I told you, that whenever you have the, whenever any of the elements, it extends or expands its valency by one more bond, it will develop a positive charge. That is by the virtue of the lone pair which is available on it. Sharing of that lone pair is what is basically there. Similarly, if this oxygen has behaved in this fashion, even this oxygen is similar to this one. So it could have been the other shift also. So what we have here is, you can have the other structure of this as O positive, C, and then you have O negative charge on the other side. So that ways you can actually make out that what are the number of canonical structures possible for a given molecule also. And so if I give you, say, let me take up the third example, which is important from your course point of view, that is the carbonate. That is the carbonate ion. Okay, there is a question to explain the resonance of the benzene again. I will do that and take up another example just after that related to benzene. But let me just complete this first. We have a carbonate ion here. The structure of carbonate ion, I will teach you how to get to the structure also using hybridization. You have done hybridization, you have done VSEPR, but then you must not have done very many examples related to the ions also. You can take out the hybridization of ions also, and you will see that the structure of carbonate ion is something like this, with the 2 minus charges are there on each of the oxygen atoms, contributing to the entire structure. Now again, you know that the negative charge is capable of forming a bond. Negative charge is capable of forming a bond. So this negative charge can form a bond here. If it forms a bond here, what will happen to carbon? 1, 2, 3, and 4 and 5. That we do not want. So what should we do? This bond has the capability of getting transferred to the oxygen atom on top of it. Clear? Again, remember, charge towards a bond and from bond towards an atom. So what we have here, you have now this oxygen developing a negative sign. We haven't touched this bond at all, so it will be negative sign here, and now this develops a double bond. Clear? Again, this negative charge can also be forming a bond. The negative charge here also can form a bond. So here in this case, this negative charge can move towards a bond like this, and the bond again directed towards an atom. Okay, so now here what will we have is, you have C O minus. This is something we haven't touched. We will have a double bond here now, and we have O minus. Okay, so this way we have 3 forms of carbonate that are possible, and that is why the general form you see in many of the books is mentioned as, you have the negative charge getting delocalized. Delocalized means sometimes it is on this oxygen, sometimes it is on this oxygen, sometimes it is on this oxygen. So it's actually moving throughout the molecule. So it can be shown like this also. You have the negative charge moving here in between these 2 oxygen atoms. You have the negative charge moving in between these 2 oxygen atoms, and you have the negative. This is only a representation. But more importantly, you should understand this structure, that your negative charge contains a pair of electrons which is capable of forming a bond, and then that bond can get shifted towards an atom. Now for the question that was there, the structure of benzene, once again, the resonance stabilization of the structure of benzene. This is what is the structure of benzene. I hope you remember what is benzene. It is C6H6. If you want me to explain the structure, you know the C6 are in a cyclopentane kind of a form, and each of the hydrogens is attached to this, and then when you have, you know that the carbon has a valency of 4, so it will be 1, 2, 3 and 4 here, then 1, 2, 3, 4 satisfied, 1, 2, 3 and 4 again here, then 1, 2, 3, 4 satisfied for this, 1, 2, 2, 3. Now the fourth one has to be here. So that is why you have the structure of benzene like this. And as I stated before, each of the hydrogens, if it is replaced by any of the functional group, it becomes chlorobenzene or phenyl chloride. Then C6H5Cl becomes phenyl chloride. C6H5 phenyl means you are talking about the substituted benzene now. Okay, that you will be doing in depth in organic chemistry only. Now here you understand that each of the bond is made up of 2 electrons, right? So I have the capability of shifting this bond towards a complete atom. So here for shifting it to a complete atom, now if A has agreed for this shifting, take it that ways. So then that means it is showing a positive behavior, and B has taken up the bond pair. So that means this has taken up this. So that is what we are exactly doing in the structure of benzene. In the structure of benzene, what we are doing is you have a double bond here. So this double bond can shift towards this atom. All right. And how does it shift towards this atom? When this double bond is shifting, you have the negative charge now on the carbon atom, and this carbon which has actually given up this bond pair will develop a positive charge, right? Now it has developed a positive charge. So here this negative charge can then form a bond. But if it forms a bond here, it has C and H here. So what will be the valency of this carbon? 1, 2, 3, 4, 5, which is not possible. So again, this double bond needs to shift further towards an atom. So it will be something like this. So next structure will then be, see, the bonds which we haven't touched can be drawn just as such. So we haven't touched this bond at all. So what we have is positive charge here. This negative charge has now formed a bond here. Okay. It has formed a bond here, and this bond has shifted towards this atom. So it develops a negative charge. Now this carbon had a negative charge. Now this, when it gives, it becomes positive, so neutral. What about this carbon? It has taken the negative bond pair from one side and simultaneously given. So negative from here, positive from here, so neutral. And what about this carbon atom? It has finally taken up the bond pair, so it becomes negative. Okay. Now again shifting the negative charge here. All right. And then this double bond will shift further to this carbon atom. Again, because of the same reason, this carbon should have satisfy the valency of 4. So here the negative charge is again towards the bond towards the atom. So the next structure would be you have this as the positive charge. This is double bond. Negative charge here. No. What happens is this negative charge is forming a bond. So the bond here, and then you again have the negative charge here. Clear? And this negative charge is now free to form a bond here. And then what about this carbon? It will be 1, 2, 3, and the fourth one is hydrogen already. So it can have this, bear this bond without any further shifting. So what we have is we haven't touched these 2 bonds now. So this carbon had a negative charge. It has now given, so it has developed a positive charge, neutral. This carbon had a positive charge. Now it has accepted a bond pair, so it becomes neutral. And in the end, you get a neutral benzene molecule, which is similar to the original structure with the alternate double bonds. Clear? Any doubts to anyone? Do you want me to repeat it again? Now here, I made you draw the structure of chlorobenzene, the resonating structure of chlorobenzene after that. Chlorobenzene, chlorine is giving electron towards to the benzene ring. Now let me take up an example where your atom is, the functional group is electron withdrawing in nature. You can do that also. Say, now that this doubt has come up, we can take it up right here itself. Say if I have NO2. All right. If I have the structure of NO2, nitrobenzene. So it will be NO2 over the benzene structure. Again, it will be C6H5NO2. Now here in this case, if it is electron withdrawing in nature, you know, nitrogen is electronegative, oxygen is also electronegative. What do you understand by electronegative? The tendency to gain electrons. So here, in this case, this bond will then get shifted towards this bond. All right, and here oxygen is taking up this bond pair. Clear? Then what happens? Why is it shifting towards this bond? Because nitrogen is electronegative in nature, and then oxygen is further electronegative. It becomes, if it becomes electron rich, oxygen, which is more electronegative, will ask for more electrons. So it will take that electron pair towards itself, and then the resultant structure would be something like, you have, now this carbon has actually given, right? This carbon has given, so it becomes positive. You have N here, N will develop, you will have O minus here, O here, and then the resonance stabilization in this case would be a bit different, that you would be doing. This is different than this. Here we were shifting the lone pair and then shifting the bond till here, right, till chlorobenzene. Whereas in this case, now your group is electron withdrawing in nature, so it is actually taking the electron density from the benzene ring towards itself. So here in this case, the bond is shifting here. So again, the next bond will shift towards this point. This is the case in case of electron withdrawing groups on the benzene ring. And then you can draw, you can at least complete this and do it in details in organic when you take it up. So here what you will have is, this will be N, O minus, O you have here, and then we haven't touched this bond at all. We get double bond here and then the positive charge here. Okay, and then the next shift would be that this bond is shifting towards this point. So what we have here is, okay, and then finally, you know that this negative charge had contained a pair of electrons, so it can also come back and get back to the same position. So there is again alternation of bonds as this. So if you now compare this and the original structure, this is only a different kind of resonance stabilized structures where your group is electron withdrawing in nature, so it is pulling electron density towards itself. In the previous cases, what we had seen was that the electron density is simply getting shifted. Here it is withdrawing the electron density. Clear? Done? Now, I mean, just to take up, if you have understood the example of benzene, I think you can take up the example of phenol. You can take up the example of phenol and try the resonance stabilized structures for this. Let me tell you, OH is again. Take up the example of phenol. Have you done all this? Now, just the last example for the resonance that we take up, and then we'll change the topic. Here in this case, please understand that again, because I have talked of electron donating nature, now here OH is also showing plus I inductive effect. So this is going to give electron towards this bond, and then this will get shifted here, just as the case of chlorobenzene. So you can just try it out quickly. Try it out quickly in your notebooks, all of you all. And I will do it simultaneously with you. Now remember that because this lone pair is shifting towards to form a bond, it will get a positive charge on oxygen and the negative charge will be on the carbon atom. Keep drawing the other structures also quickly. There will be a double bond here. Now because this lone pair is directed towards a bond and a bond towards an atom. So here in this case, what we have is Bond towards an atom means now this carbon has gained a negative charge. Now again, charge towards a bond and the bond towards an atom. So this charge will form a bond here and this bond will be shifted towards this carbon atom. So the next structure would be we haven't touched this OH positive at all. This bond is as such. Now we are getting one bond here and the negative charge on this carbon atom now. Clear? This negative will now be directed towards the formation of a bond here. We don't want this carbon to have a valency more than 4. So it gets shifted towards this. And what we get is OH positive as such. Just be careful. You should be knowing where you are shifting your electron pair. Always remember that the negative charge is forming a bond, and I repeat it again that your bond is going towards an atom. Whenever you have the shifting of the electrons, generally in majority of the cases, unless and until you have an electron withdrawing group on benzene, which was the case, which may be a bit deviating from what we are doing. So here the negative charge shifts here, and finally it goes back to the oxygen from where it started. So we'll have the next structure as, we haven't touched this bond now. This bond also is as such. This negative charge has formed a bond now, so it is here. And then you have O back to normal again. So you have, clear? Next, we'll now move on to the concept of hybridization. All right. You know that hybridization is nothing but it is the phenomena of mixing of two or more orbitals with nearly or same energies to form new orbitals. All right. See, now for the bonding, basically you have very many theories. We are talking about the phenomenon of bonding. After understanding what types of bonds we can form, we are now trying to understand the theories behind it. One is the valence bond theory. This we'll be doing in detail. The other is the molecular orbital theory. Now, in the valence bond theory, basically it is like the Lewis structures that you had drawn, where you understand the sharing of the electrons and then how many bonds are formed, what kind of bonds are formed. In valence shell electron pair repulsion theory, as you have done in details before, you have seen that it is valence shell electron pair repulsion theory. So you check the number of electron pairs and then you can easily talk about the type. You have already done hybridization and shortcuts to the hybridization also, where we talk about the mixing of the orbitals. See, another way of understanding of hybridization is what I'm going to present quickly to you, which will help you even for the Cbse as well as for the entrance examination. There is a method. Say, for example, if you have a molecule of methane, okay, what you do is you find out the oxidation state on the central atom. This is how you've been doing. Say if you have carbon, just a quick recapitulation, it is 1s2, 2s2, 2p2. You write down the ground state configuration of the atom. That is simple. Next, you find out the oxidation state of carbon. What is the oxidation state here? The oxidation state is 4. How is that? If you take it to be even, plus 4, it is a neutral molecule, so X becomes equal to -4. So whatever is your oxidation state here, that many number of single electrons should be present in the excited state. Okay, I repeat it again. What is the ground state configuration? This is your ground state configuration. 2p2, right? Now, if I'm checking the oxidation number, what is the oxidation number? It's coming out to be 4. So that means in the excited state, I must have that many single electrons, lone electrons available for bonding. Do I have 4 electrons here? No. So what will I do? I'll make one of my 2s jump towards this p, and then what will it happen? What will happen in the excited state? In the excited state, my configuration becomes 1s2 is as such, it is an inner orbital, and what I get for the valence shell is like 2s1, 2p3, right? Now here, each of these hydrogens will pair up with this, and what we'll get is the hybridization will now be sp3. All right. Based on this, have you done the comparison of methane with water and ammonia? Depending upon the lone pair and bond pair? Have you done all that? Do you want me to do it again quickly? Say if at all we have, say, ammonia, it just goes in a similar fashion. What we have is, then quickly try out ammonia, then I'll give you more. Try out after ammonia, let's just quickly compare water. All these three examples, let me tell you, are very important, because when I'm talking about hybridizations, the primary thing that you need to learn is that there are various types of hybridization. You have sp, and you can also compare them to the number of electron pairs which are available. Total electron pairs. These electron pairs may include your bond pairs plus lone pairs, or in total whatever you have. These are the electron pairs. So if you have 2 electron pairs, necessarily you will have sp. What is the shape? It will be linear. And what is the angle? It will be 180 degrees. If you have 3 electron pairs, then it is sp2. And what is the, it is trigonal planar. And this will be 120 degrees. If you have 4 electron pairs, then it will be sp3. It will be tetrahedral, and it will be 109 degree, 28 minutes, or in some of the books you will find it as 109.5 degrees also. Then you have sp3d, that is when you have 5 and you have sp3d is trigonal bipyramidal. It is not square planar, it is trigonal bipyramidal. And how do you understand this structure? Trigonal bipyramidal means that if you have a trigonal plane on the surface of the board, then one of the atom is above it and the one is at the back. Or if I am saying that if this is a plane of the table, say, then you have your 3 bonds on the plane of the table, one atom is above and the other atom is below. This is trigonal, formed on the plane of the table, bipyramidal. So you have 3 angles of 120 degrees and 2 angles at 90 degrees. So you have here 3 angles 120 degrees and 2 angles at 90 degrees, which you need to for which you need to understand the structure. All right, this is trigonal planar followed by the bipyramidal structure, that is like you have 2 angles. Then you have sp3d2, which will have 6 electrons, and then the geometry will be octahedral, and you will have all angles to be equal to 90 degrees. But again, this octahedral is also similar to a square pyramidal structure. How? What you have is, you have, say, again, consider this to be the plane of a table, right? Then you have, if your central atom is here, then you have 4 atoms on the plane of the table only. And then 1 atom is above and the other atom is below. So you have a square on the table and pyramid forming by 1 atom above and 1 atom below. So it is like this. If you have on the plane of the board, say if this is the central atom and you have 4 atoms on the plane of the board, 1b will be here and the other will be at the back of the board. So this is like a square and pyramidal. So octahedral is similar to that only, where all angles are 90 degrees. Apart from this, one of your favorite entrance examination question includes sp3d3 hybridization. Okay, sp3d3 hybridization, wherein you will have 7 electron pairs outside and the shape is pentagonal bipyramidal, and the angles are all 72 degrees. And the angles are all 72 degrees. Clear? Pentagonal bipyramidal means you have Now a pentagon forming on the plane of the board and two angles, one on top and one below. So that means you will have 5 angles of 72 degrees and 2 angles of 90 degrees. Pentagonal. Pentagon means you have the central atom on the plane of the table. Then you have a pentagon getting formed. So you have all the 5 atoms say on the, you have 1, 2, 3, 4 and 5. So this pentagon is formed on the plane of the board. Sorry, this pentagon is formed on the plane of the board. One atom is above here. So in the front, so you have one atom here and one at the back. So it is like a plane and then you have the pyramids getting formed on either side. So that is the structure of the pentagonal bipyramidal. Now coming back to this example and then we'll take many more examples of hybridization after this. So be ready. For the ammonia case, this is something that you have done already as I can make out. Nitrogen is 1s2, 2s2, 2p3. So I'm being quick in this. You have find out, the next step would be to find out the oxidation number. What is the oxidation number of nitrogen? It will be 3 minus 3 here in this case. X plus 3 is equal to 0 because it's a neutral molecule, so 0 charge. And X would be equal to minus 3. So how many electrons should you have in the excited state? 3. How many are singly present right now? Already we have 3. So we do not need to excite any electron in this case. So we can directly have H, H and H forming a bond with it. So in this case, the hybridization, as we include only the valence shell, it will be sp3. And here, this will be your lone pair of electrons and you will have 3 bond pairs. So you have 3 bond pairs and 1 lone pair of electron. And as you see the structure in this case will be the geometry will be tetrahedral only with each angle to be 109 degree 28 minutes. But because you know that lone pair bond pair repulsion is greater than bond pair repulsion, this is something that you've done before. So in this case, this lone pair will repel this bond and push it further such that the bond angle is reduced. So these two bonds come together to form a bond angle of 104.5 degrees. 107 degrees, sorry, in this case. It will be 107 degrees. I repeat the reason. The reason, as you know, is that there is a lone pair present here. And because the lone pair bond pair repulsions are greater than bond pair repulsions. So lone pair will push these bonds away from itself. So as a result of this, the bond pairs will come closer. So remember that the original geometry that you will be drawing will be tetrahedral only. But because the lone pair will push the bond pairs closer to one another and then the bond angle is getting reduced, the shape becomes pyramidal. You say that NH3 has a pyramidal shape. Then when we move on to water, you have oxygen as the central atom. What is the configuration of oxygen? Oxygen 1s2, 2s2, 2p4. All right. And if I find out the oxidation state of oxygen, what will be the oxidation state of oxygen? It will be -2. Because if you consider oxygen to be X, plus 2 is equal to 0. So X will be equal to -2. Why 0? Because water is again a neutral molecule. So X is equal to -2. And so that means I should be having 2 single electrons in the excited state which are already present in the ground state. So I do not need to excite any electron. So I will have hydrogen here and hydrogen here. Clear? Oh, sorry. Yeah. So what will be the hybridization in this case? Again, we include the valence shell. So it will be sp3, but I have 2 lone pairs available here. So then that means my structure, the tetrahedral structure, will have 2 lone pairs and 2 bond pairs. These are the bond pairs and these 2 are forming the lone pairs. Now you will include the entire reason for this. You have lone pair also. So the lone pair of electrons will repel drastically. Then you have the lone pair and bond pair. Already the lone pairs are repelling each other. They will in fact repel your bond pair also even further, that the bond angles get reduced drastically now here in this case. Okay. Right now here, what we have is, I repeat again, in case of water, again for oxygen, I repeat, it will be 1s2, 2s2, 2p4. This is the ground state configuration of oxygen. Why? Because oxygen is 8, right? So when we write down the electronic configuration, it will be this. The next step is to find out the oxidation state. When I find out the oxidation state here, for the oxidation state, it will be plus 2 plus x is equal to 0. Why 0? Because this is a neutral molecule. So x will be equal to minus 2. So now the next thing that I need to check is that my excited state or the state ready for bonding should have that many single electrons as the oxidation number. So I have 2 electrons already present, so I do not need to excite any electron any further. So let me just take the side atoms now. The side atoms are, I have one hydrogen and I have another hydrogen, and because I include only the valence electrons into consideration, or the valence shell into consideration, my hybridization will be sp3. Okay, the hybridization will be sp3, and here in this case again, that means the geometry will be tetrahedral only with the angle of 109 degree 28 minutes. Okay, and with 2 lone pairs and 2 bond pairs. So here it will be 2 lone pairs and 2 bond pairs. Now you understand that the lone pair repulsion is the strongest. So they will just repel each other a lot. Then followed by lone pair bond pair repulsion. So that means these are getting apart, getting closer to the bonds. So they will in fact repel your bond pair even further. What will happen as a result of that? Your bond pairs will come closer to one another such that the angle is reduced even further. That is 104.5 degrees in this case. And it is a bent shape. Here in this case, it is a bent shape, but the geometry remains as tetrahedral only. So when we compare the 3 structures that we have, say of methane, ammonia and water, here in this case, what did I see? This was with 4 bond pairs. This was with 1 lone pair and 3 bond pairs. This was with 2 lone pairs and 2 bond pairs. And each of them are sp3 hybridized. So what is the expected angle? It is 109 degree 28 minutes. But the angle, bond angle, is lower for ammonia. And what is the reason? Because you have 1 lone pair. So lone pair bond pair repulsions are greater than bond pair repulsions. So the bond angle is reduced because of that to 107 degrees. And for water, it is 104.5 degrees because of the presence of 2 lone pairs, where the lone pair repulsion, which is the strongest, comes into picture. Okay. Then let us take up some more examples based on it. Say now that you have done hybridization once before, let's just take up some examples directly. You work them out, start working, and then I will just discuss them with you. There is a question as to why did I neglect 2s in H2O. 2s was not neglected in case of H2O. I quickly repeat the H2O structure again. What was the H2O structure? We took oxygen as 1s2, 2s2, 2p3. Alright, this was there. So when I 2p4. Alright, so we have 2s and we have 2p4. Alright, this was it. And then when I took 2 hydrogens, I found the oxidation state of my oxygen that turns out to be -2. I should have 2 electrons ready for bonding to be available singly. They are already there. So I take hydrogens here. Why? Because these 2 are already paired up. So I cannot make my hydrogens interact with these 2. You know that in a particular orbital, not more than 2 electrons can come. This is your Pauli's exclusion principle. So here only the two singly filled orbitals interact with hydrogen atoms to form a bond, and hence the hybridization is sp3. So the doubt that was there from one of the centers that the 2s was neglected here is not correct. 2s is very much there to form your sp3. But the angle in this case is reduced because we have two lone pairs which will repel. Okay. One is left in all these cases. Why? Because it is an inner orbital which does not participate in bonding. So you have to understand whatever you have only the valence shell interacting, whereas the inner orbitals remain as such which do not participate in bonding, because of which we do not take them into consideration while deciding the hybridization. Okay, now take down some more examples. Check out, say let me give you simple examples first. You try out first one, BEF2. Let me tell you one or at least 1 to 4 questions come from this part in your examination as well. So BEF2, second try out for BF3, all right. Third try out for SiCl4, fourth try for SbCl5, fifth try for SOF4, sixth try for SF6, and seventh try for IF7. Just take down the questions quickly and then I will start discussing one by one, beginning from the top. Okay. We'll talk about the structure of the ions also once we complete this. There is a question for the structure of H3O plus. We'll take up ions also and then you will get to know as to how to decide on to the structures. Now for BeF2, just look carefully. We talk about Be. All right. What is beryllium? High He B. So it is 4. So it is 1s2, 2s2. This is your ground state configuration of beryllium. Now what is the next step? The next step is to find out the oxidation state of Be, which is the central atom. It is X minus 2 because F is minus 1. So that is equal to 0. So this implies X is equal to plus 2. So that means in your, you have 1s2 and 2s2. So that means in this particular case, you should have 2 single electrons which are not available. But you know here 2p is not filled. So what we'll do is now for now for the beryllium in the excited state, we'll make one of the 2s electrons jump towards your 2p. So what does it become? It becomes, let's concentrate only on the valence shell now. You have 2s and you have 2p. So 1 electron for 2s and 1 electron for 2p. Right? And now once you have reached your excited state which is ready for bonding, here you can just simply take up your atoms and make them bond with your central atom. So here in this case, what is the hybridization? Sp. Structure will be linear, angle will be 180 degrees. Keep revising all these so that it just rests in your mind forever. After BeF2, let's take up the next example. Done. Next is BF3. Again for BF3 it is 1s2, 2s2 and this is 2p. 1s2, 2s2 and it is 2p1, right? The oxidation state will be plus 3. What is the oxidation state of boron? It will be plus 3. So then that means if I'm talking about boron in the excited state, I need to make one of the s orbitals to jump to the p, right? So in the excited state, it will be 2s1, 2px1 and 2py1 or 2pz1 because all three are degenerate. So here it will be 2s This will be your excited state. And now you can make your, because now the oxidation state and the number of electrons in your excited state are the same, single filled. So here you can make your ref interact with this, and what you will have is sp3, right? sp3, and that will be with an angle of 120 degrees. So you can easily show it like this also. Then next, sp2, I'm sorry, sp2, s, and then you have p2. Now next for SiCl4. Now you must be wondering that sometimes you don't remember the atomic numbers. For that, let me tell you, you need to remember your periodic table group wise. All right, not just periodically, you need to remember it group wise also. And in order to remember, this belongs to the carbon family: carbon, silicon, germanium, tin, lead. So here you need to know that what is carbon: Ns2, Np2. Silicon, still you may be knowing the atomic number, but then just in case if any of the elements come from that group, so what you can do is you can just take the outermost configuration, which is Ns2, Np2, right? What is the oxidation state? X minus 4 is equal to 0 for silicon. It will be X is equal to plus 4, right? Let me just draw it, silicon in ground state. Let that be Ns to Np4, because we are just concentrating on the valence shell irrespective of the number of the valence shell. So it will be Ns2, and we have Np2, right? This is what it is. Now what is the oxidation state? It is plus 4. So how many electrons should I have singly available for bonding? 4. What will I do? I'll shift my S to P, just as in case of carbon that we do. Just the similar? Absolutely. So I'll make one shift to the P, and it becomes 2s1, 2px1, 2py1, 2pz1, right? So then what I have is for Cl, now I'll just make it bond with it. So what does it become? sp3. So SiCl4 is just similar to your methane. It is sp3. Next is antimony pentachloride, SbCl5. Which group? Nitrogen. Do you remember the groups? Let me tell you, for all those of you who have forgotten, when you talk about group 1, what do you have? Lithium, sodium, potassium, rubidium, cesium, and you have francium. In order to remember it easily, there is a formula. This is Lina Cbse Udaan. All right? You can remember that? It is Lina Cbse Udaan. All right? But you have to remember the chemistry part of it also. This is lithium, sodium, potassium, rubidium, cesium, francium. All right? For group 2 also, you have, I think, what is that? Bima ka strontium bara. All right? If you can remember it that ways. Or there may be many more ways of learning it. This is how I did it, so I'm making you learn. Remember that the periodic table can be learned in just about 2 to 3 minutes only. You don't have to look at the 108 elements with a weird look. So it is B, Ma, Ka, strontium, bara, and remember the names: beryllium, magnesium, calcium, strontium, barium, radium. The last one is generally radioactive. We do not talk about the molecules of the radioactive elements much as of now. All right. Then we move on to the P block. And in P block, what you have is you have these, right? So for this carbon, I do not have any formula, but you can remember carbon, silicon, germanium, tin, and lead. This is what you have: carbon, silicon, germanium, tin, lead. All right. For nitrogen family, it is New Zealand, Pakistan, Australia, sub, bi. Okay. Why am I telling you this? Is like the moment SB comes into your examination, you keep thinking about the atomic number. And if you do not know the atomic number, then you are stuck, right? So then if I am talking about here, nitrogen, phosphorus, arsenic, antimony, bismuth. So it is like New Zealand, Pakistan, Australia, sub, bi. You can remember that? Sure, all of you all? Then for oxygen is the simplest. Us, se, ti, po. Alright, this is the simplest. So now if you have any element, you just have to remember the outermost configuration of oxygen and you can solve it. We will just see how. And for this, you have fluorine, chlorine, bromine, iodine. Basically, these four are important. Then you have arsenite. I think it's AT or AS. I'm just forgetting, so I'm not putting. All right. And the last one is again your noble gases: neon, argon, krypton, xenon, and so on. So you have to remember this. Please remember at least the first four are very important here that I've put down. What is it? Carbon, silicon, germanium, tin, lead. Then what is this? New Zealand, Pakistan, Australia, sub, bi. And then this is simplest. Us, se, ti, po. Kabhi mat karna, but at least learn kar lena. Next, fluorine, chlorine, bromine, iodine. And then you have neon, argon, krypton. All these are noble gases. Now, if I start with something that I gave you just now, SiCl4 I've done. Now, SbCl5. So you know that it is sub, nitrogen family, antimony. All right. So what will be the ground state configuration of Sb? What is the ground state configuration here? NS2, NP3. Right. So here what I have is NS2, NP3 and ND0. You have the d orbital also available for bonding, but it is empty right now. So what will be the next step? The next step is to find out the oxidation state. What will be the oxidation state of Sb here? It will be x minus 5 is equal to 0. So x is equal to plus 5. Minus 5 due to Cl. 0 is the charge on the entire molecule. So it is x is equal to plus 5. So that means in the excited state, how many electrons should I have singly? 5. Okay. So here it will be Sb in the excited state. You have S here, you have P here, this was the ground state. You have D totally empty. So you can make your S jump from here to the D, and in the excited state, what you get is you have NS, NP and ND available. So that will be 1, 2, 3, 4 and 5. So satisfied? Now in the excited state it's confirmed that it will be this. Now it's just similar to what you have done. You must have done PCl5. Now this is SbCl5. So what is this? What will be the hybridization? You start from the outermost. It is S and this will be Cl, Cl. Cl will go with each of these singly filled electrons to form sp3, 1, 2, 3, 4 and 5. sp3d. All right, sp3d. And you know what is the shape of the, geometry of a sp3d? Trigonal bipyramidal. And here, even if you've done, I think you can lend me your ears again to listen to me, that SbCl5. So that means 3 Cl are on the plane of the board. 3 Cls are on the plane of the board. One is above the plane of the board, one is below. But still I need to represent it on paper. So let this be Cl above and let this be Cl at the back. All right. Don't just leave SbCl3 here directly. Why? Because it is not for your understanding, but you even have to make the examiner understand. So it will be SbCl5 with 3 angles 120. And you know that these are the equatorial bonds. These are the equatorial bonds and these are the axial bonds. And which bonds are weaker? Axial bonds. Why are they weaker? Generally, there is a question also for PCl5. This is like a question asked almost in all the examinations. PCl5, it is the same structure absolutely. You just have to replace the antimony with phosphorus. Here in this case, when we talk about antimony, it's like PCl5 going like this. The question is, PCl axial bond is longer than PCl equatorial bond. Why is that the case? Because you have more repulsions for this 90-degree bond. You have more repulsions for this 90-degree bond than the other repulsions, right? So because these two bonds suffer greater repulsion, so that is why they are longer. So remember that the axial bonds are longer than the equatorial bonds. Then, so our SbCl5 is sp3d. Next we have SOFO. In SOFO we have sulfur, which is again now, even if you don't remember the atomic number and you remember the group wise configuration, what is oxygen? NS2NP4. So sulfur will also be NS2NP4, and then you just go about writing down the ground state configuration. It is like, right? This is for S and P. Now O4, what is the next step? I will be finding out the oxidation state of sulfur. Now here in case of SOF4, this is X. What is O? It is -2. What is F? It is -4, equal to 0, which is the charge on SOF4. So X will be equal to +6. I have still my d orbital available for bonding, which is empty. So what I can do is, I can make my d orbitals, S and p electrons to jump to the d. So in the excited state, I'll just put down for the excited state directly. In the excited state, I will have NS, NP, and ND. So what I have is, I had initial one as this. So I'm making 2 electrons jump from here to go here. So how many do I have now? 1, 2, 3, 4, 5, and 6. So done. 6 electrons are available for bonding. Now, how many atoms do I have? 3. Now, keep paying attention carefully. No, I have 5, sorry. So, how do we go about doing it? I have SOFO. So, each of the atom goes with each of the single electron. So, done. Then, I have 1 electron still available, right? I have 1 electron still available. Till now, whatever examples we have taken up, we always had a lone pair of electrons. We never had an extra electron left over like this. So what do we do with this? First, let us see the kind of hybridization. What will be the type of hybridization? It will be sp3d. All right. So in this case, I will have SOFO means say O, something like this. You expect it to be like this, right? Now, what about this extra? This always, whatever, if you have a single electron left over, that constitutes your pi bond. That forms your pi bond. So, in this case, where will the pi bond be formed? Here. So, the basic geometry of SOF4 should be looking something like this. And then because of the repulsions and all, it actually sums up, the geometry will be here trigonal bipyramidal only, but ultimately it becomes kind of a square pyramid on one side. Not bipyramidal, square pyramidal. Clear? Now the next one, SF6 is really simple. For S, it is again, I'm talking about SF6 now. What is it? NS2, NP4, right? The oxidation number will be 6, just as in previous case. So I am directly putting down the sulfur in excited state. It is similar to the previous case only. So what I have is so after making the electrons jump, this is what I get. For F6, it's really simple. You make start from the S and what you get is sp3d2. Okay. Next, for IF7. Now for IF7 again, you must be wondering, I don't know the atomic number of iodine. Do you have to think about the iodine's atomic number? No. Why? Because this belongs to your halogen family, fluorine, chlorine, bromine, iodine. You know the configuration of the general group. What is that? It is NS2NP5. It is NS2NP5. So for iodine, the ground state configuration will be simple NS2NP5. So when I draw that, it will be NS2 and NP5, right? NS2NP5. I still have my ND available. Let me check the oxidation state in the second step. What will be the oxidation state? It will be X minus 7 is equal to 0, where minus 7 is from the 7 fluorine atoms. So X will be equal to plus 7. So how many electrons should I have singly available? 7. So what will I do? I'll make this jump to D, I'll make this jump to D, and I have another electron. So I'll make all these 3 jump to D. So then I will get 7. Let me check iodine in excited state now. So you have NS, NP, and ND. So it will be 1, 1, 1, 1 here, 1, 2, and 3 in D now. Correct? Check 7 single electrons. Condition satisfied. So quickly I have to put F7. So not even, I mean, for the exams, entrance exam, you don't need to draw all these structures. It will go in your mind only once your 7 are there. You know, all the 7 will be utilized for bonding. So the total will be now sp3d3. All right, it will be sp3d3. And for sp3d3, it is trigonal, pentagonal, bipyramidal. So you have 5 f1 2 3 4 5. So this is like a pentagon on the plane of the board, 1f above and 1f below. So that can be shown as this f is say above and this f is say below the pentagon. So you have pentagon in one plane, 1f above and 1f below. Clear with IF7? So now let's take up some more examples, complicated ones that you can do. But before that, do you want to note down sp3d3? You will be able to do on your own. But before that, please recapitulate the periodic table in your mind once again, because the periodic table is really important to solve any example for hybridization. And how do you go about doing it? The first group is Lena, Cbse, so lithium, sodium, potassium, rubidium, cesium fraction. What about the second one? B mark A, strontium, bara. Repeat it. B mark A, strontium, bara. What about the next one? It was carbon, silicon, germanium, tin, lead. Repeat it. Carbon, silicon, germanium. Didn't you have food? Carbon, silicon, germanium, tin, lead. What about the next one? New Zealand, Pakistan, Australia, sub by, include India also, but not here. Right? New Zealand, Pakistan, Australia, sub by. What is it? Nitrogen, phosphorus, arsenic, antimony, bismuth. Clear? Next is oxygen, sulfur, selenium, tellurium, polonium. And next, fluorine, chlorine, bromine, iodine, astenine. And the last one is for the noble gases that we can also solve. Right? Now take up some quick examples of hybridization which are asked in the examinations also. Okay. Take up SO4 2 minus. Then the question that came for H3O plus should be solved on your own. Alright, first take up these ions and then just try to solve that on your own. ClO3 2 minus. ClO3 will be minus. Then try PO4 3 minus. Or don't do phosphates, complicated. ACO Cl2 and try for XeO3. Try one more, SnCl2. Did we do SnCl2? Have we done SnCl2? Just try working it out. All right, now for sulfate, can we try it out? Sulfur is NS2, NP4. This belongs to the oxygen family. So the ground state configuration will be NS2, NP4. All right, so it will be NS2, NP4. Okay. Now for the oxidation number of sulfur and sulfate. What will that be? X minus 8 equal to X sulfur. Just look at sulfate. It is X. All right. You have 4 oxygens. So for one oxygen, the charge is minus 2. What is the valency of oxygen? It's minus 2. 2 generally. So 4 into 2 minus 8. What is the total charge on the molecule now? That is minus 2. So X minus 8 is equal to minus 2. So what will be the oxidation state now? X is equal to plus 6. Plus or minus does not really make a difference in hybridization because you must have that many number of single electrons available for bonding. So here you have X is equal to plus 6. So that means you should have 6 electrons available for bonding finally. So here 6 means that you need to make one jump from here. That makes it 1, 2, 3 and 4. Right? You make another one jump from 2 to D. So it becomes 1, 2, 3, 4, 5 and 6. So that solves our purpose. I repeat, what was the first step? You write down the ground state configuration quickly. NS2, NP4. Once you've written the ground state configuration, the next step is to find out the oxidation state. How do you find out the oxidation state? You consider the central atom to be X minus, you have 4 oxygen atoms, so 4 into minus 2 is equal to, what is the total charge on this molecule? Minus 2. So what does it become? X minus 8, sorry, X minus 8 is equal to minus 2. Okay, so X is equal to plus 6. And according to the funda that I told you, you must have as many number of single electrons as are available as is your oxidation number. So here it will be 1, 2, 3, 4, 5 and 6 when I make P and S jump to D. So sulfur in excited state will be NS. Let me just draw this orbitals only directly. It is S, P and you have D here. Now excited state ready. Now how many atoms are available for bonding? We have 4 oxygen atoms. So we take the first oxygen atom, it goes with it. Next oxygen atom goes with it. Third and fourth. So what is the hybridization now? The hybridization is sp3. And what about these two? I told you these are not the lone pairs. Lone pair means you have a pair in a particular orbital. These are the 2 single electrons. So they will be contributing to pi bond formation. Let us see how they will be contributing to the pi bond formation. How? We'll just quickly look at it. We have, for the pi bond formation, here what do we have? we have sp3, so that means it will be a tetrahedral geometry. So it should be something like S of O, O, O and O, something like this in a flying wedge projection. If I draw like that, it will be like this. Now you have two pi bonds to get formed. They will get made with any of the two oxygens, any of the two without bias. And what is the total charge on the molecule? It is 2 minus. So either you may assume that the 2 minus is on either of these two, or you know now about the phenomenon of resonance also. So you know that minus charge can get delocalized on other oxygens as well. So what you can do is draw a square bracket, represent this 2 minus charge outside. So this 2 minus charge is also very important. So sulfate is sp3 hybridized. That is more important for you to know, because this question normally is not asked in the Cbse exam, but directly for your IITs that you have. Okay? You want me to repeat it again? No. Can we move on to the next example? Try ClO3 minus quickly. Chlorine belongs to the halogen family. It would be NS2, NP5. We're looking only at the valence shell. The inner shell orbitals will not participate. So here in this case we have NS2 and NP5 like this. Now ClO3 minus, let me check the oxidation number now. It will be X minus 6 is equal to minus 1. Why minus 6 now? You consider your Cl to be X. You have 3 oxygen atoms, so 3 into minus 2, that will be minus 6 is equal to minus 1. Minus 1 is the charge on the molecule. Till now we had been taking 0, 0 for the neutral molecules. So here X will be equal to plus 5. So how many electrons should I have in my excited state? This was the ground state. So in the excited state, chlorine will be now, you have the d orbitals also available. So in order to make it 5, I can make jump 1 from P to D and another one from S, right? So the excited state will become now, you have S, P and D. So it will be 1, 2, 3, 4, 5, 6. This is NS2NP5. So we have this one, oxidation number. So we can make this jump here. So 1, 2, 3, 4, and 5. Right. Okay. So now what we have is you have 1, 2, 3, 4, 5. I'm sorry. So you make 2 electrons jumps from P to D. And so here we have the configuration as NS, NP, ND. ND is 2, NP is 3, and now NS is 2. So here what we have is you have your, how many atoms available? 3. So let's make them O. You have Cl. What are we doing? ClO3. So we are doing ClO3. So we have 3 oxygens available. So you have O, O and O here. So the hybridization will be sp3. And what about these two? This will be 2 pi bonds will be getting formed. And what about this one? Lone pair of electrons. So now remember, now this is one example which has lone pair of electrons also and pi bonds also. Look at it carefully. What we have is Cl. Cl, the normal configuration is NS2NP5. We just simply fill it in NS and NP. We see that D is still available. We find out the oxidation number. What is the oxidation number of the central atom in here in this case, which is chlorine? The oxidation number is X minus 6 is equal to minus 1, which is the charge on this ion. So you have X is equal to plus 5. So now you have to make sure that there are 5 single electrons in the excited state. How do you make sure? You will make the 2p electrons jump to the other side. Thank you for corrected me. Here in this case, when you have 2p electrons jumping to D, it becomes 1, 2, 3, 4, 5 single. Now we are ready to make it get bonded with the oxygen. So you have 3 oxygen atoms. So 1, 2 and 3 quickly get bonded to it. What is the hybridization now? It is sp3, right? And 2 are available for pi bonding. Now when you have to understand the structure, it will be ClO3. So you know that it will have a lone pair. This is your lone pair. O, O and O here. And you have 2 pi bonds on any 2 oxygens without any bias, right? 2 oxygens and you have ClO3 and you have a minus charge. So that can also be represented not just like this. You can also represent it like minus. Okay. Try out the next one. Selenium oxychloride. That is SeOCl2. Selenium belongs to which family? Selenium belongs to which family? Oxygen. So what will be selenium? In the ground state, it will be NS2 NP4, right? What was it? SeO Cl2, right? NS2 NP4. Now the next step is to check the oxidation number of selenium. How do you check it? X. What is your oxygen? -2. What is your chlorine? Chlorine is -1, but how many chlorines do you have? 2. So it will be -2. So it is equal to 0 and X is equal to 4. So how many electrons do you need to have singly available? 4. So what will you do? You have what will you do now for the excited state? We can make 1p orbital, 1p electron jump to D. So here in this case, what I have is, all right, I'll have 1p here. So it will be S here, P and D. Now I'm talking about the excited state. How many atoms? O, Cl2. So O, Cl2. So what will be the hybridization? Again, sp3 only. sp3, so that means it is tetrahedral. So this is Se. You have a lone pair, you have oxygen, you have 2 chlorine. So your lone pair is taken care of, 2 chlorines are taken care of, you have an oxygen. What about this? It will form a pi bond with none other than oxygen. So this is your SeOCl2. Done? Next for XeO3. This is again a very important example. Try it out for XeO3. I'll just check. Xenon is a noble gas. So the outermost configuration, outermost shell is like complete. Follows the octet rule, whatever. You just see that. So it is NS2. The general configuration for that group is NS2 NP6. Okay. So now here, when you check up for the ground state, it is NS2 and NP6. So it is completely filled. What is the next step? I will find out. I am taking up XeO3. The next step is to quickly find out the oxidation state. A question? In ClO3, why NS2 is not jumping? Because we find out the configuration, or we find out the oxidation number, and if that oxidation number is getting satisfied as such with just the jumping of the p electrons, then there is no need to touch the NS. But that NS will be included in the hybridization, and if we have a pair of electron there, that will be contributing to the lone pair of electrons. Clear? Any other question that is there? How will we decide to whom should we give the double bond? See, for deciding onto the double bond, you should be knowing the valencies. You know, chlorine is 17. So if you remember from your 8th grade, it is 2, 8, 7. So you know that the valency is 1. So it can form only one bond stably with any other atom, right? Or it can just have one more electron. It just needs one more electron. Then for oxygen, you know, oxygen, the valency is 2. So if you see that in your structure, as in the previous case, Se, you have O, you have Cl, and did we have a lone pair of electrons? I have a short-term memory. So it is like we had a lone pair, this is what it was. Then we saw that there was a pi bond electron that was available for the pi bond formation. So how to decide, you know, chlorine will have a valency of 1. So we definitely will not put it here, it will just make it unstable. And we know that oxygen can have a valency of 2. So what we are going to do, it will make it absolutely stable. So we, without any doubt, it's like a clear-cut thing generally that you can put your double bond. Sometimes you have, say you have 3 oxygens and say only 2 electrons are available for bonding. Then in that case, you can arbitrarily put your double bond anywhere. Not just I have been putting it like this because I like symmetry, but otherwise you could have put it like this also, right? Without any bias, because if you have symmetrical atoms, then it is not a problem to decide. When you have different atoms, then only you have to decide, and that can be decided easily by the valency of the atom. Okay? Next, we were doing XeO3. I come back to XeO3 again. In XeO3, what is the outermost configuration of xenon? It is Ns2, Np6. Clear? Now, what is the oxidation state of xenon? It is X. Xenon will be treated as X. What about O3? It will be minus 6 is equal to 0. So, X is equal to plus 6. That means I need to have, so P to D, P to D, and then P to D. This is how it will go. So now here, when I now take it to the excited state, in the excited state, it will be, so this is Ns, Np, Nd, all right? 1, 2, 3, 4, 5, and 6, right? Now Ns, please remember that this Ns is not excluded. It is a part of our valence shell and it is participating in our bonding also. So now I have O3. Be careful. So now O3 means start from the single first electron. So you have O, O, and O. So what will it be? Sp3. Sp3. And what about these 3? Pi bond. So whosoever asked that doubt now should feel happy that all the 3 oxygen atoms are getting a pi bond each. But here in this case, sp3 means tetrahedral, so it will be some kind of this structure, O, O, and O. This represents the first 3 bond pairs that we are getting. Now for the 3 pi bonds, 1, 2, and 3. So it is a pyramidal shape and the geometry is tetrahedral only, but because of the lone pair bond pair repulsions, the bond angles do suffer here also. Okay. After having discussed xenon oxide, trioxide, we can take up more examples of noble gases also, right? You know how to do it, you will be flexible. Remember that here if you have a lone pair, that will be in your structure getting reflected. And in the end, if you have single electrons, they will be your pi bonds that will be formed in that particular geometry along with some bonds which are already available. Clear? Now, the last example that I had put was SnCl2. Let's quickly take up that, and last 3 example is xenon, and then we'll just take up one more topic for today so that we comfortably get over with this in the next class, this entire topic. Next is like I take up SnCl2. Sn, which group? Carbon, silicon, germanium, tin. So this is tannous chloride, tin. All right. So here, if this is carbon family, so that means it will be Ns2, Np2. So quickly in the ground state, I make it. It is Ns2 and Np2. Now For the oxidation state, X minus 2 is equal to 0. It's neutral, no ion is mentioned here. So here in this case of X minus 2, it will be X is equal to plus 2. 2 electrons are already available. So nothing is to be done here. I will just take this ground state as such to be available for bonding. 2 atoms Cl, so it will be Cl and Cl. So what will be the hybridization? Remember, Ns is included. Many people were asking this question. So it will be sp2, and the geometry will be trigonal planar, and you will have in that trigonal planar, you have a Cl and a Cl, and you have a lone pair of electrons. Okay. Now, because we've done at least one example of xenon, let me give you more examples based on xenon. Just try out XeF2, XeF4, and XeF6. Quickly find out, because these hybridization are asked. Let me tell you, these will again be taken up in your 12th grade. And this will help you then. You will be able to write down, do at least the noble gases in one go, if you have understood how to solve for the hybridization of these structures. Try out one more, XeO2F2, because now you have understood the concept of hybridization also. For the pi bonds and lone pairs, try out XeO2F2 also. And let me tell you, based on VSEPR also, if you can make out the number of electrons, you can easily talk about the hybridization. And then I saw that you already have the shortcut to hybridization also. This was only an in-depth understanding as to how your structures are decided, just in case if you get any extra structure from the atom for which you do not remember the atomic number. Starting with XeF2 quickly now, I think many of you must have already solved. It is NS2 NP6. This we've already seen. So what will be the oxidation state in case of XeF2? It will be X minus 2 is equal to 0. So X is equal to plus 2. So the ground state was something like this. NS2 and NP6. This was my NS, this was my NP, and this is my ND. So this is NS2, NP6, and I need to have only 2 more electrons available. So for 2 more electrons to be available, I can just make one of my P jump to D. I can make one of my P jump to D. So here in this case, what will be my F? It goes with this and it goes with this. So what will be the hybridization? sp3d. How many lone pairs? You can see 1, 2, 3 lone pairs, 2 bond pairs, and this is sp3d. So then that means I have xenon trigonal bipyramidal structure. So I have a trigonal planar on the plane of the board, 1 fluorine above and 1 fluorine at the back. So it will be, this is xenon with 3 lone pairs, first lone pair, second lone pair, third lone pair, and then I have 2 fluorines, 1 above and 1 below. Because these 2 fluorine atoms are the ones which suffer maximum repulsions, we are not placing lone pair here. If I place lone pair here, then lone pairs will give a maximum repulsion to all the bond pairs, and we want a stable structure. So the shape will be linear, but the geometry is trigonal bipyramidal. Okay? Then quickly for the next XeF4, similarly, we'll just take it up. For HCF4 again, I'm just changing it here, saving my time. You know xenon is Ns2Np6. HCF4, the next step is to find out the oxidation number. What will that be? X minus 4 is equal to 0. So this implies X is equal to plus 4. So then that means now in my normal ground state, I need 4 electrons to be singly available. So I'll make one P to go to D and another P go to D. So then that will be this 4 single electrons available. Quickly take up the 4 fluorine atoms. Now you have to be quick. Once you've learned, be quick at it. So it will be sp3d2. With how many lone pairs? You have 2 lone pairs and because all the angles are at 90 degrees, now you can have xenon fluoride to be a square planar structure because all the angles are 90 degrees. So it doesn't really matter where you're placing your lone pair. So let one lone pair be above and the other be below. It will be some kind of a square planar structure. The shape is square planar, if you can see clearly. And you have 2 lone pairs which are above and below. Done? Now for XCF6 again, it's very simple. Now for XCF6, you know xenon is Ns2Np6. For the oxidation number of xenon, it will be X minus 6 is equal to 0. And so this implies X is equal to plus 6. So here I need to have 6 electrons. So my initial ground state configuration is Ns2Np6 like this. I need to have 6 means I will be making each one jump to 1. So it will be 1 electron goes from here, 1 from here, 1 from here to form this. And what I get is 6 fluorine atoms will now get bonded with 6 single electrons that are available. So what we have is the hybridization with Ns included. It will be sp3d3. That is pentagonal by pyramidal. All right. And that means I have pentagon means 5 in a pentagon. With each angle it's 72. You have 1F below and there is a lone pair on the top. All right. Then the last example that I'll take up today for hybridization, and next time I'll take up more questions from your direct papers. Done with this, sp3d3. Next is XeO2F2. Again, your xenon is Ns2Np6. Now in XeO2F2, you check the oxidation number of xenon. What will that be? X minus 4. Why minus 4? Oxygen is minus 2. So minus 2 into 2, minus 4, minus 1 into 2. So that will be minus 2 is equal to 0. So X is equal to plus 6. So it was something similar to the previous case only. So Ns, I have Np and Nd available for bonding. So this is Ns, Np, Nd. I know that in my ground state it is completely filled. But if I want to have 6 single electrons, I'll make 3p jump to 3d orbitals. So 1 from here, 1 from here, 1 from here. And it becomes this. I have O2, F2. So O2 and F2. So what is my hybridization? It is sp3d. And what about this? What is this? This is a lone pair. All of you all. Last example, I won't give you any more examples. What is this? This is lone pair. What about these two? These will be forming pi bond. I have sp3d, so that means I have, say, some kind of a structure where I have a lone pair. I have fluorine atoms above and below, single bonds. These are oxygen. And then I have 2 pi bonds to be formed. So this will be my structure. It will be kind of a seesaw structure. The shape is seesaw here in this case. when I decided on to the initial geometry of trigonal bipyramidal, the shape is seesaw. Why am I saying seesaw? Because see, this is XC. So looks like a seesaw. So this is it. All right. Where you have to understand that this is one plane and this is above and this is below. Right? Okay. Now I think even for any of the examples that you can just try it out and you will be able to solve for the hybridization. And next, I think we can talk about you have already done VSEPR. That is also again deciding onto the structure or geometry depending upon what you have in the lone pair kitty. You now know that if the total bond pairs are this many, you can easily decide on to the type of hybridization. But sometimes if you get complicated examples, then rather than sitting on to decide on to the valence electrons, you can quickly work it out by the hybridization and just state that this is the hybridization, and if whatever angle or whatever is asked, you can always tell. Next, we can talk about, see, we have already seen, we have been talking about covalent bonds, bonded structures only, because we are talking about sharing and then forming of the bonds. When I talk about the covalent bonded structures, there is and we have also seen ionic bonds. Now see, just understand this particular case, that when I talk about ionic bonds, it is the interaction of an electropositive element with an electronegative element. Right? So if I have, say, a cation and an anion, A plus and say B minus, then in that case, both of them are associated with a kind of an electronic cloud. Are they associated? Both are associated with an electronic cloud. Now, when I talk about covalent bonds, I see, or when atoms have same size. So generally, there is no distortion of the structure. So we say that in this case, nothing is affecting the other one, and we say that there is no polarization. I will just explain the meaning of polarization to you. There is no polarization. Polarization means because they are of equal size, equal strength, they are just not affecting each other. Okay, but when I am talking about, say, let the size of the cation be smaller. If I have the size of the cation in an ionic bond to be smaller, say this is smaller and you have a big sized anion, then in that case, this small cation has the capability of distorting the anionic cloud, right? It will come closer, it will interact, change the shape of the cloud, and then that means it is interacting with the anionic cloud and distorting. So just understand the meaning of polarization. Polarization means it refers to the distortion of the ionic cloud of one ion with the other. That means if one ion is distorting the cloud of the other, then it is known as polarization. All right. Then if this is polarization happening in this case, then it eventually leads to the formation of some kind of an interaction between the two ions, which is referred to as some kind of covalent character now coming in. See, because if we are interacting, normally in ionic bonds, what happens? There is a complete transfer of electrons. If the two electrons are interacting and getting shared, then we say that there is some kind of a covalent character. So remember that I am talking about a concept of polarization. What is polarization? It is the distortion of the ionic cloud with the other. Now, someone may ask that if an anion is getting distorted by a cation, cation also can get distorted by an anion, right? But the point is it is already small in size. So the distortion here in this case is negligible in comparison to the distortion of the anion. So that means जितना छोटा cation होगा उतना ज़्यादा वो effective होगा in distorting. So that means polarization will be more. And जितनी polarization होगी उतना मेरा covalent character is coming into the picture. Clear? I repeat it again. Ionic bonds सबको पता है. What are ionic bonds? They are the ones which are formed by the complete transfer of electrons. Now I am talking about two ions, say positive and negative. They are associated with an ionic cloud. My small cationic cloud is capable of distorting my anionic cloud. This distortion is known as polarization. जितना ज़्यादा distortion होगा उतना ज़्यादा covalent character is getting introduced. So basically this is summed up in a title of Fajan's rule. Now in Fajan's rule, basically we are talking about the polarization of one ion from the other. Generally anionic cloud getting distorted because of the cationic cloud. And here we see greater the polarization, greater will be the covalent character getting introduced into my ionic bond. Clear? Ionic bond is positive, negative, covalent is sharing, but when I am talking about polarization, I am talking about a covalent character. So I am repeating it again. You also repeat it. Greater the polarization, wake up, greater the polarization, greater is the covalent character. Greater the covalent character, lower will be the melting point. Because there will be trends which will be asked. So this is a very important funda that you have to remember in very many questions. Questions that will be asked to predict the trend of melting points. You cannot remember the melting points, but you can predict the trends. I repeat, greater the polarization, greater will be the covalent character, and greater the covalent character introduced into my ionic bond, lower will be the melting point. Okay. So now Fajan's rule basically state that polarization is very high for small and highly charged cations. Please remember, for small and highly charged cations. This is very important. Highly charged is also important. Say if I take up two examples, CaCl2 and say NaCl. See here in this case, what is the basic thing that you are going to look at? See, the anions are the same in both the cases. Look up all of you all to the board. Here the anions will be the same. Anions are the same. Sodium belongs to group 1, calcium belongs to group 2. Sizes are comparable, right? Because even if you talk about the size, calcium will anyways be smaller in size. Because on going down the group, size increases, and on going from left to right, size decreases. But here one thing is absolutely clear. What is the charge on sodium? It is +1. What is the charge on calcium? It is +2. So what is my Fajan's rule stating? That the polarization will be more for small, highly charged cation. So because the charge density is more on calcium, so then that means there will be more covalency in case of calcium chloride or more polarization in case of calcium chloride. If the covalent character is asked, which has more? This has more than this. But if the melting point trend is asked, this is more than this. Clear? This clearly holds good for what I have told you. Greater the polarization, for polarization greater किसमें होगी? The one which has a higher charge, Ca2 plus. Greater will be the polarization. So this is more covalent in nature. And greater the covalent character, lower will be the melting point. So melting point of NaCl will be much higher than that of CaCl2. Got it? Let us take up another example. Check up for BeCl2 and CaCl2. So which will have a smaller size here? You can remember the second group, Bima ka, strontium bara, you remember? Now B is beryllium, calcium is below, so calcium will have a bigger size. Do we want a bigger size for polarization? Small size, high charge density. So which will be more polarizing in nature? BeCl2. And so the melting point of BeCl2 will be lower than that of CaCl2. Clear? This is for the small and highly charged cations. So you can get any example. If you remember the periodic table, you know on going from top to bottom, size increases, and on going from left to right, it decreases. So if you remember just that, you will be able to solve all such things. Small size and high charge density of the cation favors polarization. Clear? For the Fajan's rule, the first point is done. Second, large and highly charged anion. So now you can get the trend for either predict the trend for the polarization, or you can also get to predict the trend of the melting points also. For the Fajan's rule, I am telling you, Fajan's rule is nothing but it talks about the degree or the creepance of the covalent character into your ionic bond, and that refers to nothing but the distortion of the anionic cloud by the cation, which is decided by some points, the first of which we have just talked about. Next is we want the size of the anion to be bigger, because जितना साइज बड़ा होगा अनायन का उतनी आराम से वो डिस्टॉर्ट होगा, उतनी पोलराइजेशन ज्यादा होगी. ये चीज तो क्लियर है. नाउ लेट्स जस्ट टेक अप an example straight away. You have to predict the trend for polarization. LIF, LICL, LIBR and LII. You have to predict the trend. LII followed by LIBR followed by LICL followed by LIF. Why? Because they belong to, lithium is common in all. So what do we have to compare now? The anion. And if I have to compare the anion, I have to look at the size ka trend or the charge density. Charge density in sub mein it's -1. So what is left? Size. For the size, I will be looking at fluorine, chlorine, bromine, iodine. On going from top to bottom, size increases. So polarization would increase. Now if I say predict the melting point trend, it will just be the reverse. So polarization trend will be maximum for LII, then LIBR, then LICL, then LIF. For the melting point, the highest melting point will be that of LIF with least covalent character. So it will be like this. Alright, this is for the melting point trend. Remember that you can get to know about the melting point trend now, and also the amount of covalent character that a particular atom possesses with the help of your Fajan's rule. Right? Now the next third one is, the third factor that decides is the pseudo noble gas configuration, electronic configuration of atoms. It is generally called the pseudo noble gas configuration of atoms. Either you just have to understand that if your d orbital is getting filled, then because d is poorly shielding, shielding ka matlab pata hai? D is poorly shielding, then in that particular case, what we basically have is that it will have more interaction with the clouds. So because d electron is getting filled and it is poorly shielding, there will be greater polarization if your d orbital is already filled. Any atom which has say 18 electrons completely filled or more than that, they will, or the d orbitals getting filled, they will have greater polarization than your p block compounds. Got it? I repeat, the ones which have a pseudo noble gas configuration, they will have a greater polarization than the other compounds. So wherever a d orbital is getting filled, remember that that compound will show greater polarization, and greater polarization means greater covalent character, and greater covalent character means lower melting point. That is clear. So let me just take up an example for this to illustrate clearly. In Ca, you do not have any d orbitals. Silver belongs to your d block, right? So here in this case, you will have the polarization to be greater in case of HgCl2 than CaCl2, as a result of which the melting point of CaCl2 will be greater than that of HgCl2. Okay? Now, let me tell you, Fajan's rule not only help in predicting, we can take up n number of examples in this also. Fajan's rule, you just have to remember, not only helps in predicting the melting point trend, not only helps in predicting the amount of covalent character, but also helps in deciding the solubility. For solubility, please understand, this is again a very important concept. For solubility, what you need to remember is that your like dissolves like here in this case. This is a separate topic that can be taken up in a proper one class, like dissolves like. So then that means if my covalent character is more, if my greater polarization means greater covalent character, then that means the non-polar nature is also more. Right? What do you understand by polarity? Separation of charges. Right? What do you understand by non-polarity? It is generally no separation of charges and you have more of sharing. So generally covalent compounds are non-polar in nature. What about Cl2? It is non-polar in nature. What about your benzene? Your benzene is non-polar in nature. What about your water? Water is polar in nature. You have partial negative charge here, partial negative, and you have partial negative charge here, positive and positive. So water is polar in nature and these are non-polar in nature. So if you are given any non-polar solvent, say you are given any non-polar solvent, because these are the kind of questions that normally come for your entrance examination. Say if you are asked, you are given say ethanol. Ethanol is not really polar in nature, so how will you decide on to the solubility trend in it? Now greater the polarization, greater will be the covalent character, and the one which is really covalent in nature, that will be easily soluble in your non-polar solvent. Say if I'm talking about say ethanol or if I'm talking about benzene, so whenever I am talking about any of these, if I'm talking, so now what will be the trend for solubility here? The solubility trend here would be your LII will be the most soluble, your LIBR would be soluble next, and maybe LIF is insoluble completely because LIF will have the least polarization with the least covalent character, means more ionic character. So that means your ionic will not dissolve in non-polar solvent. So your LIF will not be soluble, maybe very least soluble. So Fajan's rule is not only helping you in predicting the covalent trend or the melting point trend, it also helps you in deciding on whether a particular compound will be soluble in a polar solvent or a non-polar solvent. That depends and you have to look into the question carefully. Alright. Now if I ask you, say, I give you examples of, you have CuCl, AgCl and NaCl, and you have to predict whether they are soluble in water or not. That is the question. Now based on Fajan's rule, you know NaCl is completely ionic. Alright, least polarization. Here Ag and Cu belong to D block. So then that means their polarization will be much greater than that of, this is for polarization, their polarization will be much greater. Why? Because of the electronic configuration of their cations. They will be they will have greater polarization. Greater polarization means higher covalent character, means less ionic character, or they will be non-polar in nature. Now, if you talk about the solubility of non-polar compounds in a polar solvent, will they be soluble? No. So, what will be soluble more? NaCl. Right? So, before I wind up, let me tell you and give you some tips of, let me just quickly recapitulate the Fajan's rule. For the Fajan's rule, remember that there are 3 points essentially. The very first one is that the size of the cation should be small and it should be having high charge density. We had taken up 2 examples. Like for example, if we take BeCl2 and CaCl2, their Cl2 is common. We will concentrate on the size of the cation. Which is smaller in size? Beryllium. Because B mark R, you remember that they belong to one group. So it is, beryllium is smaller in size, so it will show greater polarization. So BeCl2 will be having more polarization, more covalent character than your CaCl2. Next, if I talk about charge density, say I take up an example of CaCl2 and NaCl, then Ca has higher charge density, so it will be showing more polarization than your NaCl. And more polarization means more covalent character, right? Introduced into your ionic compounds. Otherwise, these are ionic solids only. ionic compounds that we are talking about. Next, second point for in the Fajan's rule is that if you have large and highly charged anions, then that also favors your polarization. And what is that? If our large and highly charged anions favor polarization, then that would mean that greater the size and greater the charge density. And for this, we had taken up this example only of LIF, LICl, LIBr, and LII. Cation is common, so we will be looking at the size of the anions only. Charge is the same, -1. So if I talk about the size, I know on going down the group, size is increasing. So greater the size of the anion, greater will be the polarization. So the polarization will be maximum in case of LII, then LIBr, then LICl, then LIF. Then after this, what we have is the electronic configuration of the atoms, wherein we say that if you have any molecule which has a cation with a pseudo noble gas configuration with the d orbital also getting completely filled or getting filled. Now, because the electrons are poorly shielding in nature, they allow for greater polarization, and hence we see greater polarization in such cases. And we had taken up an example of HgCl2 simple with, I think we had taken it up with CaCl2. So Cl2, Cl2 common, concentrate on this. Clearly here, this belongs to your D block. So we'll have greater polarization of Hg here than CaCl2. There is another question. I mean, before I complete this, the last one is also done. Now there's another question. What is the shape of XeO2F2? What is your xenon? Xenon is a noble gas, so its configuration will be NS2 NP6. Then we check up the oxidation state of xenon. What is that? X 2 OS2, so -2 into 2, that will be 4, so -4. F is -1, so -1 into 2, so that is 0, so X is equal to +6. Alright, so that means in the excited state I should be having 6. So here in this case, 1, 2, 3, 4, 5, and 6. I'll make 3 p electrons jump to 3 d electrons, right? And then when I start forming the bonds, I have 2 O and I have 2 F. So here in this case, I have 1 lone pair with 4 bond pairs forming sp3d structure. This was the question, the shape. So the geometry is sp3d. So here sp3d means Xc, I have O and a lone pair. See, lone pair O and O. So that form in the trigonal planar part. Planar means it is the plane of the board. Now, one fluorine will come here in front of the plane of the board. One fluorine will go at the back, but I will still show it to you. Say this is the trigonal planar. You have one fluorine on top and the other fluorine below. But I still have 2 electrons which are left. These 2 electrons will contribute to the pi bond. So where will the pi bond go? Fluorine has a valency of 1, so definitely not to fluorine. So it will come here and here. And the shape will be seesaw. Seesaw is that swing that you actually must have seen in the parks around. Alright, so XeO2F2. What is the hybridization of C2H6 is the next question. In C2H6, what we basically have is, see, always remember that C2H6 is also an alkane. Now for today, I can quickly tell you that remember that whenever we have the carbon around with 4 bonds, it will always be sp3 hybridization. Alright, it will always be sp3 hybridization. So, and for alkenes, I will just quickly do C2H6. For alkenes, what we have is C2, say H4, it will always be sp2, which has a double bond. sp2 is necessarily on the double bonded carbon atoms. So both of these will be sp2. And when you have alkynes, for alkynes we have C2H2 types and triple bond. So the carbon atoms which have a triple bond will necessarily have an sp hybridization. Here itself I'd like to tell you, if you have some atom like this, you have CH3 and CH. If this is one of the alkynes, this carbon is sp hybridized, this carbon is sp hybridized. Now because this carbon has 4 bonds around it, it will be sp3 hybridized. Okay, just remember that. Do not get confused that alkene hai to all the carbons will be sp2, alkynes hai to all the carbons will be sp. Just in case there is any carbon which is singly attached to the 4 bonds, then in that case it will just be sp3. So this is sp3, this is sp, this is sp. Now coming to the structure of C2H6. In C2H6, what we basically have is carbon in the ground state will be 2s2, 2p2. Right? Again, now here in this case, the normal carbon configuration in the excited state is always taken as 2s, and you have 2p2 here like this, 2s2 and 2p3. You make it jump here because carbon will necessarily have an oxidation number of 4. Why? Because it will have 4 bonds around it. So here in this case, what we basically have is that each of your hydrogens, C2H6 is your ethane. So here when you decide on to the geometry, it will be one carbon getting attached and you have H6. So each of the 3 atoms will go necessarily with this. All right. This carbon will be involved in the sigma bonding with the other carbon atom. All right. So it will be C2, right? So this will be one head of the tetrahedral structure and H6 with each of these angles to be 109 degree 28 minutes. Remember that whatever electron is left, we have taken 3H with one carbon. Similarly, the 3H will go with the other carbon. And there is one electron still left for the S or maybe with the PZ. That will be involved in the sigma bond formation for this CC. Clear? Okay. So here what we have is on all these carbons, I mean the angles here, all of them will be 109 degree 28 minutes between any 2 bonds. Right? Why NaCl is more polarizing than CaCl2? When we talk about CaCl2, our Fajan's rule, all right, NaCl, first of all, directly look at the anion is same ClCl, usko compare karne ka koi fayda nahi hai. We'll be comparing our cation. So here Na is in +1 charge, kyunki Cl is -1, Cl2 is -2, so your Ca will be +2. So this has higher charge density. Greater the charge density, greater will be the polarization. पोलराइजेशन में और पोलैरिटी में फर्क है. पोलराइजेशन अगर इसमें ज्यादा है तो कोवेलेंट कैरेक्टर भी इसी का ज्यादा होगा. Polarization means the distortion of the anionic cloud generally by a cation. Okay, I mean it can be the other way around also, but because anions are generally larger in size, that is why their anionic clouds get distorted. Okay, done. So now please remember the Fajan's rule and we'll take up examples, more examples of this in the next class. Thank you very much.